Okay, guys, that was a beautiful start with some singing in the morning. So let me open this session. Welcome, everyone. Welcome, people from the workshop, from faculty, maybe also some external ones, or they might come later. Welcome also everyone that is watching us on YouTube. So we are starting the 2 last days of JSALT, and these 2 days will be full of presentations. It's up to me just to present the practicalities. So essentially it's very simple. We will have part 1 in the morning done by the role-playing agents, by the Play Your Part team. Part 2 by Emma in the afternoon. But first of all, we will have Sanjeev presenting an overview of the workshop, of also the most important results of the teams. Some practical stuff, we have not arranged for any lunch. We already know the area. There are a couple of restaurants around. So if you are here just for these days and you don't know the surroundings, just join any of the FIT or of JSALT people. We also did not arrange any lunch, any dinner today. The dinner will be there, the big one, tomorrow. And if anyone doesn't know the place, we are in the biggest lecture hall at our faculty, D105. The facilities are just one stair below, one floor below. You can either use the staircase or the elevator if you have some problems with walking. And an important note, this event is being recorded and everyone is going to be public, so don't be rude. Okay, I think that's where I stop, and I would like to invite Sanjeev, the emperor of the whole show, to present the summary.
Thank you, Hansa. Yeah. So thank you, Hansa. I will save my thanks for Hansa for the end of tomorrow, because a lot of work goes into getting this thing together, and you won't believe how much he's done. But let's leave that for tomorrow, because there's a lot more to say about it. Let's move on with my presentation. Okay, let's see if this can be made to work. Okay, we have our first problem. Just a second. Okay, and let's start presenting, and let's go down. Ah, there we go. Perfect. So I'm Sanjeev Khudanpur, and along with Hansa and Paula, I'm one of the organizers of this year's summer workshop. But of course, there are 4 different teams, as I'll tell you about very soon. And they're led by Ricard, Lukáš and Samuele, Ramani and Santosh, Yannick and Fethi. So this presentation today and tomorrow is basically a joint effort by us getting a whole bunch of other people to do good work. So let me just get into that. So first, just for the record, how did we get here? What did we accomplish? So getting here, as I told you in the opening presentation, is a long journey. So back in the 50s, the Center for Communications Research in Princeton, which is part of the Institute of Defense Analysis, they had been holding these 10-week summer workshops. They called them scams, to tackle cryptology problems. And they've had a long record of success. And some people from IDA carried this over to the speech and language field in 1993. So for the first time, Jordan Cohen and Jim Flanagan organized a workshop at Rutgers at the Center for, I can't even remember what CAPE stands for anymore. Yeah, and they followed it up with another one in '94. So that's where the summer workshops began. And they became the Hopkins workshops essentially in '95, because Fred Jelinek, who had been leading a very well-known speech group at IBM for a long time, came and became the director of the Center for Language and Speech Processing at Hopkins. And the workshops kind of followed him, and he has set the framework for the method of how we do these workshops all these years. So '95 was the first JHU workshop. One of Fred's first innovations was that, unlike Rutgers, which mostly had senior people, they had students too, but the emphasis wasn't getting researchers together. He brought in a whole bunch of PhD students, made them very integral, and that was my association with Johns Hopkins with the workshops. That's when I came there as a grad student. So what I was saying about this, standardization of the workshop recipe, if you will, how do we have these long summer activities and how to make them successful. This really is a year-long process, and Fred sort of institutionalized it over many years, from 95 until he passed away in 2010, so that's like 15 years. So really it begins with planning way back in September. So as soon as we finish this workshop, we're going to start planning for 2026. We send out a call to everybody in the community and say, hey, what are cool ideas that are ready for being pursued in a multi-institutional collaborative way, not something that one group or one university can pursue, but which really needs people from all over. And we ask for ideas, just one page. Sometime in October, there's a deadline. We screen out the impractical ones. Some of them are just not practical as workshop topics because they may involve 6-8 months of work together rather than 8 weeks. Others are not practical because sometimes we get proposals from graduate students saying, this is my thesis topic, let's have a workshop on it. Not quite the idea of a workshop. But then most of the others come through, and we have a meeting in November where we discuss the ideas, figure out what might be practical. And our criteria are things like, is this problem ready for attack? Is this an idea that is likely to succeed? Is this something that is best done by collaboration rather than one group pursuing it by itself, and so on and so forth? And then once we do that, we essentially pull out the team leaders and the core teams in November. We try to get funding for it. I'll say something about funding in my last slide. And then we sort of start making sure we have enough critical mass of senior people. Because once you, when you're a grad student, all you do is your research, but once you've grown up, you have children, you have family, you have responsibilities. So getting away for 6 weeks or 8 weeks is not trivial at all. So we try to finalize people who can actually be here for 8 weeks. We pick the grad students with the help of the senior people. Fred used to joke, there's no point inviting a professor because if you don't invite their student, no work gets done. So you then get grad students involved with the help of the professors. We select undergrads because we always believe that they bring new ideas. They try things that grad students and senior people are too jaded to think about trying. Our former president at Johns Hopkins once said something like, yeah, I gave the problem to a bunch of undergrads and they solved it because they didn't know that it couldn't be solved. So things like that. So, and then finally, in March and May, we also try to get all these teams to physically meet all together. Because remember, the core ideas and the team leaders get settled in November, December, but many other people join afterwards. So it's very critical to actually meet face-to-face for a day or two and sort of figure out what you're going to do together and get to know each other. In fact, the other day I was talking to Ricard and he said, yeah, everything went well this year. I said, what is the one thing you could change? He said, well, due to geographic constraints, we ended up having a meeting where all the Europeans met in Europe and all the Americans met in America, and we had a day-long meeting over Zoom. No good. We really should have been in one place. So it's really important, and we try to push this. And then, of course, the summer begins in June, and we have the 2-week summer school and the main workshop. And then by the time the workshop ends, we ask all of you guys to write reports while we start doing the next year's workshop. So this sort of cycle was set with Jelinek and me between 95 and 2010. He passed away in 2010. I decided to continue and have had help from lots of colleagues every year. The one thing I did differently was I decided to take the workshops on the road because many, many years it has always been in Hopkins. So 2014 was the first year we had it outside Hopkins. It was Prague, partly because Fred was from Prague. Actually, he was from Kladno, I think, which is near Prague. And we had it over there, and that's when we also gave it its name. We started calling it the Jelinek Workshops. 2015, we held it at Seattle at the University of Washington. And then we realized that having it back at Baltimore regularly is very important because there's a lot of institutional history in the, the staff and the administrators at Hopkins. They know all the important things that need to be done. So if you go away for too long, that institutional memory gets lost. It's very hard to write these things down anywhere, even if you try. So we said, okay, we'll do alternate years. So 2015 was Seattle. 2017, we went to Pittsburgh. We had it at CMU. 2019, we went to Montreal. 2021, there was a minor glitch. We couldn't do the workshop at all. And so we skipped it. And 2023, we went to Le Mans. And 2025, we are now in Brno. So this is how the workshops have been. And we hope to continue this 1 year at Baltimore, 1 year somewhere else. Next, this year, what all did we do? So as I said, the proposals were solicited back in September. So this is the call for proposals that went out. And as you can see, we had a bunch of topics in mind, very broad, no restrictions. People could propose anything. So we knew that LLMs have taken the text processing world by storm, so we wanted to address any challenges that continue to be there with LLMs, like their auditability, controllability, interpretability, explainability, and so on and so forth. Speech processing, we still knew that robustness is a huge challenge. Even though Alexa and Siri seem to work reasonably okay from a distance, it's because it's very directed dialogue and it's very cooperative. We knew that multimodality is very, very critical because all these speech and vision and other languages were starting to come around and the technologies were starting to sort of coalesce, if you will. And finally, like, responsible AI has always been important. So these are the broad areas, but within that, we solicited topics from everybody. And as you will see in a minute, we got a very nice response, and we have teams working on one or more of these topics here in this summer. So the planning, as I said, began in the fall. We received 24 ideas, a few were screened out, a couple of authors withdrew because one of the things that's, again, very important about how we come up with the workshop topics is that you actually sit down and have intense discussions about the pros and cons. And unlike reviewing a proposal for a grants agency where you send it in, some anonymous reviewer reviews it, and you just get back an up-down answer, maybe with a few comments, this is interactive. You actually get to face your reviewers and say, why don't you like it? Say, well, this data said it's artificial, you should get some real emotions. Oh, where do you get that? Well, okay, I have an idea, there's this corpus. So it's a very process that's been very successful. Now, why doesn't every grant agency in the world do it? It's simply not practical, it's not scalable. But if you wanted to pick 4 projects a year, yes, this can be done. If you're an agency that was funding 400, this is not scalable. But that's one of the powers of the workshop. You can do innovative things. We invited people to the planning meeting. We invited a lot of reviewers. So in addition to the authors, there were if you take 46 minus 14, that means there were 32 other people. And nice balance, about 17 academics from outside Hopkins, 17 people from industry, 9 Hopkins faculty. Out of that, only Paula and I were organizers. The other faculty just acted like faculty and reviewers, and we had a few government people. And we ended up brainstorming these ideas and discussing them. Started Friday 6 p.m., worked more or less nonstop till Sunday noon. We slept a little bit, yeah. So that was all good. And finally, we got 3 very strong projects. And then, while all this was going on, JSALT has had a longer-term collaboration with a European project called Esperanto. And so in parallel, we developed an Esperanto team, which got an ad hoc review. And therefore, we finally have 4 teams for the summer workshop. Right? So the projects are the EMMA team, the end-to-end multi-channel, multi-talker ASR team. This is led by Lukáš and Samuele. And they have 6 senior researchers, 7 PhD students, 2 undergrads, and 7 affiliates. And this time, unlike the opening presentation, I was pretty strict. I said, somebody makes it on this list if they were involved in the research and present in Brno for at least 1 week. So there are a lot of remote collaborators, a lot of teams. You'll see longer lists when the teams present their team membership. But I'm pretty strict. I'm like, if you're not physically here, you might as well be collaborating with anybody anywhere else in the world. Good for the teams, but don't make my stats. The other team, as you just heard from Hamza, is looking at role-playing agents and how to interpret them, how to control them, how to make them do things you want them to do. This is led by Ricard Marxer, and it has 7 senior members, 8 grad students, 3 undergrads, 3 affiliates. The audio general intelligence team is led by Ramani Duraiswamy and Santosh Kesiraju. It has 3 senior members. Paula couldn't make it, so even Paula doesn't count in my stats because she wasn't here for a week. 9 grad students, 2 undergrads. By the way, this is just to tell you the physical presence of people. It doesn't mean these remote people don't contribute, so don't get me wrong. And a number of affiliates. And finally, the TTS team, led by Yannick and Fethi Bugares. It has 10 senior members, 9 PhD students, 9 students. I think we have a couple of masters, but I count them all as grad students, and 4 affiliates. And so this is a team. Altogether, there are 85 people who are resident here. So if you put some average of 5 weeks or something, because some senior people were here for 6 weeks, students for 8 weeks, a few people for less than 6 weeks. It's some enormous number of person years. I don't know how many. I'll have to do the math. Maybe 7 or 8 or 10 person years worth of work, all in 8 weeks. So where are these people from? So I did some statistics yesterday. I tallied up everything. The good part about being in Brno is that I actually now know all of you, so I actually could figure out, I made one error, I'll tell you about it in a minute, about which country everybody's from. So this is the map. We have 22 countries represented. The USA still leads. It's the one with the most people. That's partly because, you know, the workshop originated there. France is number 2. Go France. Then Czechia, India, Spain, 7 each. And actually, I initially thought there were more Czechs, then I realized 3 of them are Slovaks. So unfortunately, I had to ding them and put them in a different bucket. Argentina, China, you can see the list. And I made an error. I put Marc Delcroix in Japan because he lives and works there. It turns out he's Belgian. So Japan will go down by 1 count and Belgium will enter the list. So it'll be 23. Continent-wise, Asia has 9 countries. Let me see, Turkey, Georgia, Iran, Kazakhstan, India, China, Malaysia, South Korea, Japan. Europe actually has 9, once I correct for Mark's Belgian nationality. Spain, France, Belgium, Switzerland, Germany, Czechia, Slovakia, Poland, and Greece. And 2 from South America, Brazil, Argentina, 2 from North America, USA, and Cuba. Demographics, we're doing okay for computer science, not okay where we would like to be, about 25% women. But what is good is a lot of the women are up and coming in the field. So this demographic will hopefully change as time goes. But it's, it's something we're working on and it'll keep going. In terms of preparation, a little less than half have PhDs. So these are senior researchers, team leaders, and things like that, people like that. About the remaining 53% are students, of which 7 are undergraduates, and the remaining students are PhD or master's students or grad students. So nice mix of different academic preparation levels. In terms of affiliation, the workshops have had this trend that even though it's an academic exercise, we tend to work on the the cutting edge of technology, trying to figure out new things. And so companies really invest in them. So they don't just give us money to support the workshop, they actually send people. So remember I said these are only residents, meaning they were there at least for a week, and many of them for 5 and 6 and 8 weeks. So 80% are academics, the rest are non-academic. And I didn't put everybody in industry because some people are from non-profit or government-supported labs and things like that. So I just said, okay, other. So they're not from a degree-granting institution, but they're not in a profit-making company either. So that's the last little sliver. And last but not the least, of the 85 people I mentioned, 80% have been here full-time. What I mean by that is if you're a student, you're here for 8 weeks. If you're a senior person, you're here for 6 weeks. And about 1/5 of them have been here for less than 6 weeks for various reasons. But they've been physically present. So that's the distribution of the residents. So you can, again, use these numbers and calculate how many person-years of effort have gone on in these 8 weeks. But this is all fabulous because when so many smart people put so much effort together, you can almost guarantee that good things will come out of it, as you'll see in a few minutes. So what do these 85 people do over here for 8 weeks, right? Well, so the first 2 weeks, we spent learning and teaching. We had the summer school. Every day there was a little bit of a theme, and 2 or 3 people decided that they will contribute their valuable time to create tutorials and train the students, participants of the workshop on things that they may or may not know much about. By the way, every day there were some students in the group whose research area this was. So they got a little bored, but they helped by actually teaching. And then everybody else learned. So by the end of the 2 weeks, everybody knew something about speech recognition, speaker identification, diarization, computer vision, evolutionary machine learning, all the way down to the 4 specific teams, Emma, TTS, Playopard, and Augie. So these are the first 2 weeks. And then we rolled up our sleeves and got busy doing work. So these were the next 6 weeks. Of course, we were mostly working, but also all sorts of little things went on in parallel to keep our minds stimulated and going. Most important of them was cookie breaks. So we took a break at 3:30 every day to eat cookies in the excellent student lounge, which has a foosball table and a pool table and a music room. But other than that, of course, we had plenary lectures. So the green boxes say external speakers coming and trying to, enlighten us about new developments in the field. We had one each in the first 3 weeks, and the fourth and fifth weeks, we had 2 plenary lectures each. We decided not to have any this week because we're having this event. We had weekly updates. Other than the first week where we had the opening presentation, we had one every week, and this week, this is the update. This is the final report, if you will. We also had a special meeting with the undergraduates. We call it a brown bag lunch. It turns out to be pizza lunch because Martin and Jarek were very helpful in getting us pizza, and we did that. And then, of course, we had social outings. We had these no-host dinners where we discovered Czech food, and I even discovered an Indian restaurant that I like, another one I kind of like, and so on and so forth. So this was all fun. And of course, now we are here today to do the presentations. So in the morning, we'll have the first team, afternoon, second team, and tomorrow morning and afternoon, the third and fourth teams. So for the plenary lectures, just to kind of have it on record, we had Mark Delcroix talk to us about target speech and sound extraction. He's been working on this for many years at NTT. Barbara Schluper came and talked about cross-layer models of conversational speech. And people online, just in case you're thinking these are layers of a neural network, no, these are linguistic hierarchies, and there is neurological evidence that the brain processes speech in this way. So she was talking about connections between phonemes and morphemes and other lexical-like units in speech processing. Ramani told us about how, backprop and gradient descent and all are not just something we do in deep learning. They're actually connected to a whole set of ideas in machine learning, and he talked about differentiable models in machine learning. Loic Baralt came along from Meta. Meta is, of course, doing a lot of great work in AI in general and in speech and language in particular. Loic tried to persuade us that they've got the next great thing called large concept models instead of large language models. We remain to be persuaded, but it was a great talk, and we learned a lot. Sorry, Loic, I don't mean to rag on you. Hervé was here. He's part of the team, but he also is the co-founder of Pianote.ai. He calls it Pianote, but I think it should be Pianote because it comes from Python. And he talked about speaker diarization, his long association with it. He wanted to call it a love story, but then he realized it's about the training loss that you use to train the model, so he called it a loss story. We had Javier Serra from the University of Pompeu Fabra in Barcelona. He talked a lot about music understanding with large models, music information retrieval, and music generation. This connected us with some things we're doing in the workshop as well. And last but not the least, Jordan Boyd-Graber was here, and he talked about how AI models often do useful things, even though they may not do things exactly as we want them. And these were the set of plenary talks. But enough for the other stuff happening. What actually happened in the workshop? Well, so I'll go through each of the 4 teams, and I'm going to give you this highlight so that you can step back a little bit and think about what you're going to get in the next 2 days. This is not giving you their final results. This is more of a teaser. This is my take on what the teams have done. The team leaders may have a different opinion, and they'll get 3 hours to talk about it. So you have to listen to me only for 2 minutes per team. So the first team, which is going to present right after me today, is the team that worked on dialogue generation. This team's main challenge was, can we use large language models to produce synthetic dialogues which are very realistic, which are factually correct, which reflect the kind of dialogues people have? And if you could do this, you could do many things with such a tool or such a capability. You could use it to train humans. So for example, doctors often train by talking to model patients who can fall sick, as somebody said the other day, 40 times a day with 40 different ailments. You can use it to train customer service agents, so just people who interact with the customers of a company. You can use it to train AI models, because very often interpersonal dialogues have a lot of privacy issues. People don't expect their dialogues to be recorded and fed to machines. So it's good if you could synthesize them rather than try to get permissions or, worse, violate people's privacy expectations. So those are the reasons why you want to work on these. And they showed that LLMs are actually quite terrible at generating dialogues. They have, it might sound very doctor-patient-like, but if you really look at it for a while, it generates 6 of them. It's almost the same dialogue every time, and you'll see examples of it. And the real way to go past it is to start driving them with personas. You say, hey, This is what the first participant is, this is what the second is. And so you'll see nice evidence of how persona-based prompting enables generating realistic dialogues, diverse dialogues, and so on and so forth. But of course, what is a good dialogue, right? So they investigated many facets of dialogue quality, and they created these multifaceted evaluations, both manual evaluation of dialogues and automatic. Because remember, once you decide you're going to do dialogue generation, you can't sit and have somebody read and annotate every dialogue, so you need automatic methods. So they created automatic methods for naturalness, persona adherence, clinical relevance of a dialogue, and so on and so forth. Of course, text is one part. A real dialogue needs to be enacted in speech, so they worked on speech synthesis. And the challenges here are that traditional speech synthesis thinks about producing one speaker's voice in a quiet environment. This needed to be multiple talkers with other beeps and boops going on in the doctor's office, and so on and so forth, and so on. And they worked on that. Also, if you synthesize dialogue and it's not going well, how do you correct it? How do you make it do what you want? So they looked at aspects of steering dialogues, it's basically to control adherence to persona, for example, right? And last but not the least, there are many people working on many things, but they have a beautiful framework to put it all together. It's called S-Dialogue. I was very happy to see it, something that actually started 2 years ago in Le Mans, because there was a team there working on dialogue flows and learning how to use them to do various things. And that work has continued, and that toolkit is now something on which all these pieces of the work that the team is doing can be pulled together. So you'll hear about it right after my presentation. The second team, which you'll hear about from this afternoon, worked on end-to-end multi-channel, multi-talker speech recognition. So their challenge is when you have multiple talkers, there's overlap speech, there are background noises, there isn't enough training data, because it's hard to really transcribe multi-talker dialogue. So it's a pretty challenging problem. So they worked on many things. Their starting point was this idea called diarization conditioned speech recognition, which is something many members of the team had worked on about a year and a half ago. The idea is take a standard speech recognition system which expects one speaker at a time, and when you give it multi-speaker speech, tell it who's speaking when, and let it work through the speakers one at a time. So they developed a new, basically they improved it to the point where it's the state of the art now in many benchmarks. And the original ideas were meant for encoder-decoder models. Now it's been extended to RNN transducer type models like Parakeet. So the other thing they did is they improved multi-channel diarization, because you're going to rely on diarization to improve speech recognition. You got to do good diarization. Diarization is this process of figuring out who spoke when. So they developed new state-of-the-art benchmarks. One of the key things was that they were able to use multi-channel data, which is relatively new. It's been done, but only in the recent past. And also they extended this diarization conditioned processing idea to speech separation, speech enhancement, so you'll see some results on that. They developed new training criteria. One of the funny things is if people talk, one person at a time, it's easy to write down what they said because that's the order in which they said it. If two people talk and they overlap each other, in what order do you want to write down the words? It's kind of tricky because if you interleave them, it doesn't make sense, but if you leave them separate, it's not the truth. It's not what the model is seeing. So we developed they developed some new criteria on how to deal with the multi-talker training to elegantly handle overlap speech and so on and so forth. They investigated using LLMs. Why? Well, you have to, kind of, in this day and age. Two reasons, two scenarios, rather. One is when you've done your speech recognition, but you want to figure out who spoke which parts. That is like a post-processing. But better still, why don't you integrate it with the recognizer, where the language model does both, helping with the transcription and helping with speaker attribution. And last but not the least, they've created a leaderboard. It's meant for collaboration, but a little bit of competition does help in collaboration, doesn't hurt. So there's a leaderboard now where a number of ideas in the team have been exercised, but it's going to be open to the whole world. And we'll see if we can get more people to crack this problem open. So that's the second team. The third one, you'll hear from this team tomorrow morning, worked on speech to text, or text to speech, I'm sorry. So one of the key foci for them is to work on very low resource languages. And low resource, there's a saying about what's the difference between a language and a dialect, and it's usually an army and a navy. So many times there are things which are called dialects, but which are really slightly different languages. So you really need to work on various dialects and various varieties and various realizations of a language, and synthesis in them is not easy. So they created a number of data sets in many low-resource languages. Bengali is a big language, but there aren't many resources. Central Kurdish, Cuban Spanish. I don't even know where Kabyle is spoken, Sarawak Malay, Tunisia. So these are the languages in which we now have data. It's 50 plus, like minimum 2 hours in each language, and some of them have more than 2, 10, 12, one of them is 30, I think. They created a new evaluation toolkit. Because one of the things is evaluating speech synthesis is very hard. There's a whole bunch of metrics, and when you have lots of resources, the metrics pretty much track and do similar things. But when you have very low resource settings, you want to measure all the things because you want to know exactly what is working and not working. And it was important to have a single toolkit that sort of incorporates all the evaluation metrics. They even came up with a new one we're going to hear about from Natasha. And it supports also extrinsic evaluation, because sometimes synthesis alone may not be great, but it might serve a function. It might convey the meaning that you want to convey. So you can test it automatically by putting it in the translation setting rather than getting humans to listen. So that ideas like that will be shown. They implemented a neural codec called TiCodec. It is apparently the best and the greatest and latest since sliced bread. And they incorporated it into the speech brain tools because that's commonly used in the community. It's capable of streaming, and it's capable of controlling. I think Yannick called it time invariant properties, but after talking to him, I realized that I should call it long duration properties. So things like gender, prosody, which are not expressed frame by frame, but which need to stay faithful in a longer segment of speech. And last but not the least, they have created new models, trained new models, and released them. And these are capable of all kinds of cool synthesis, including accented voices. So you might hear some demos, actually. We'll see what they do. And last but not the least, the team that worked on audio understanding, General Augie. This team essentially created a nice new benchmark. There are 5,000 new question-answer pairs. They exercise emerging perceptual abilities of these models, not just the standard stuff that people have worked on in the recent past. Many aspects, including aspects of speech processing, aspect of music understanding, processing long-form audio, not just 30 seconds at a time, but 10, 20 minutes at a time, and spatial audio. Like, can you understand audio in a 3D setting? And it goes beyond multiple choice questions, because most past benchmarks were just multiple choice. And here we have free-form answers possible. And of course, once you have free-form answers, evaluation becomes difficult, because multiple choice, you know what the right answer is, you can evaluate a model. But in this case, it's a little harder. So they created a nice technique, if you will, or a nice model, where essentially you have the correct answer and a rationale, so that when an alternative answer is given to judge whether it's correct or not, you only need text-based capabilities. You don't need yet another audio language model to judge whether this audio language model is good enough. So that's the new methodology. You'll hear about it. They have created or gathered, I don't know what's the right word, new data sets, because unlike text-based language models where you can, well, not you, companies have gone and crawled 1 trillion or several trillion words of text. It's not easy to get that much audio, even for the pre-training stages. So they have collaborated with people and put together nice new pre-training data sets on which we'll do new training, we'll try out new training ideas. And finally, they have some new training criteria that they've implemented, look promising, one called GRPO, another one which is don't tokenize the audio for an LLM just like without any context, tokenize it in the context of a query or a question so that you can answer the query that you need to answer. So this is everything you're going to hear about in the next 2 days. But putting a workshop together like this costs money. So you haven't paid much attention to it. Only Honza and I have been worrying about it. So how much money does a workshop cost? Well, here's the short answer. So this workshop cost us $700,000 in cash, about $200,000. There's an estimate, really a guesstimate, if you will, in computing credits, and a whole bunch of other in-kind support, which is even harder to quantify than the computing credits. So these are our sponsors. Google and Johns Hopkins are the two biggest at about 30% each. Esperanto, the European consortium with whom we've been associated for several years, this is the third biggest. And then we had some leftover money from Microsoft. Actually, Microsoft people don't even remember, but this is money they gave us when Fred was still around. And it was sitting unused, and I decided we'll use it. Amazon gave us some money. The Faculty of Information Technology actually gave us cash to support some of the activities. And NSF, ByteDance, there's a Czech project called OPIAC, and Telefonica through the Eloquence project. There are many sponsors. So when you write your papers, please remember to say that this work was at JSALT, and I'll give you some language saying many sponsors contributed to the workshop and so on and so forth. And within JHU, actually, I owe a particular thanks to my dean, because the yellow part, which says COE, is actually a sponsored project, but the gray part is actually my dean trusting me and saying, okay, I'll give you this money because I know you'll do good work. So this is real Hopkins money being used for our research.
Does that mean that you're scraping the bottom of the barrel? Because normally the department wouldn't support stuff.
Oh, no, I have a good history with so Dan's asking, am I scraping the bottom of the barrel? The answer is, I have a long history with my dean. He sees how the money comes and goes. He's seen it for 30 years. So he knows in steady state, this is a good operation. So no worries. Absolutely not. All right. Okay, computing. So we got a lot of support from the French National Cluster. We got support from the Pittsburgh Supercomputing Center. This is the US equivalent of this. We got help from, CLSP has its own computing. We set aside a little bit of it for the workshop. We got about $50,000 in credit from Amazon, AWS credits. And the small company, Fish Audio, gave us some GPUs, I think an 8 GPU node or something. So many people helped with computing. So like I said, none of this is cash. None of it comes into our hands. Hard to put a value on it, but you can count how many tens of thousands of GPU hours you have, put some nominal price on it. And like I said, this is a real guesstimate. I have no idea how much it is. And last but not the least, people support us without compensation. So a lot of BUT facilities come for free. So where we're going to have our dinner tomorrow night, it's a huge, beautiful facility. You'll see it. If this was a commercial world, you'd be paying for it. But BUT said, yeah, you're our people, come enjoy, things like that. JHU administration, all these contracts and this and that have to be signed. Some poor lawyer somewhere is reading it, editing it. We're not paying them. JHU covers their cost. Gemini gave us some API credits. And of course, Hansa, Paula, and I, we put in a bunch of effort. So basically, these are all the unsupported effort. And the effort of all the senior people whom we're not paying any salaries. Your companies and your universities are covering your effort. So there's a whole bunch of unsupported effort that goes into JSALT. So it's a massive exercise. All right, so let me stop here and just say we're back to the technical program again. And at this point, I'll stop. I'm not expecting questions unless there's a burning one like Dan had. Any other questions that are really something you want to know right now? No? Okay, in that case, let me hand it off to Ricard. Ricard, you'll take it from here, maybe use the other computer? Okay.
Hello. Okay. So first of all, thank you very much, Sanjeev. Thank you for organizing this, Sanjeev and everybody else that put this together. And so I'm Ricard Marxer. It's a big pleasure for me to be presenting the work that our team did, the Play Your Part team. After 1.5 months of really hard work, here we are, trying to show off what we did. So I'll start with a little introduction, giving you a bit of motivation and why we are doing all of this. I think Sanjeev gave you a little taste. I'll try to go a bit more in depth in it. And then I'll cover what are our main contributions and what's the outline of the presentation. And then I'll let the heroes actually do the work of presenting what they did. So what are we trying to do in our team? We are trying to simulate how humans act in conversational settings. Okay? We want to see if the generative models that we have seen doing very impressive capabilities in linguistic and many other tasks, can we use them to continue a conversation the way they continue normal text? Okay. Can we get them to act like real humans when playing a conversation? And we don't want to stop in the verbal content, on the text and the conversation. We want to go a bit further. Can we get the prosody, the tone of a speaker? Can we actually get the other acoustic cues like coughing, laughter, emotions? Can we get the variety of humans when doing dialogues? And because we get to that point, well, let's actually render these dialogues into speech and into speech in the real environment where they happen, with the sounds, with the room acoustics, all of this. So this is the goal we set ourselves to do, and we will see that it's not an easy task. But let's start with, why do we do this? Why do we generate dialogues? Okay, so there are many reasons. Sanjeev gave a few of them. The first one is synthetic data. I think most of us here are machine learning engineers, and we know how difficult it is to gather data. And for certain cases, it's just simpler to make the data than to actually solve the problem. So an example of that would be the CAPTCHAs, right? The CAPTCHAs is very easy to make a CAPTCHA from a text annotation. It's actually a bit harder to go back. That's why we use them to protect sites. I think they're not a good protection nowadays anymore, but anyway, there are other situations in which we actually need data and we don't have it. This is cases like the medical domain, where data is not made publicly available. We cannot get it. There's also situations in which we like to have control on the data on which we train our systems. There might be biases on the data that we have in the real world, and we might want to mitigate that biases so we can control it. Or maybe there are scientific studies in which we want to see how much a factor of the data affects the result. Another case in which we would like to have synthetic dialogues is when we are trying to assess the performance of a conversation. For instance, in an emergency call center, we would like to know how things are working. Can we make them better? Or in diagnostic procedures, like can we improve the way doctors conduct diagnosis? Another case is in training professionals. I mean, this is the example I was telling and Sanjeev referred to. Like in the 1960s, they were really happy to get a patient that could get sick 30 times a day. And actually this was useful because we were able to train doctors with those patients. Okay. So now we fast forward a few years, we still need to train doctors and we have many more students to train, and we need these patient simulators to be able to conduct this training. There's even games of these. In Steam we can find a game called Medical Diagnostic Simulator. The issue with this game is a very, very bad game according to the raters, so I think we can do better. Let's see. Following on this trend of medical conversations, this is our main focus, is doctor-patient conversations. Having a focus helps us, and in this case, this particular scenario is very useful because it's challenging and interesting even with a two-party conversation. Even when there's only the doctor and the patient, it can be very difficult because it has specialized knowledge by one of the speakers. It has a very big diversity in the other speaker, like the patients. It can be relatively long, and it is goal-oriented. They have a reason to be there. Okay? The other aspect is that in medical domain, data is very, very scarce. So having data, simulating data will be very useful. And finally, of course, healthcare, we all know how important it is for society. So having an impact there will be important to all of us. But it is not an easy task. And let me show you a video that Thomas put together using one of these state-of-the-art video generation, where we asked them to make a doctor-patient conversation, and let's see how it goes.
I understand your concerns, and we're going to work through this together. Thank you. Of course. Now, about the next steps.
So as you can see, it's not straightforward to generate a doctor-patient conversation, and these are the kind of tasks that we are set to do.
I understand your concerns, and we're going to work through this together. Thank you.
Let's continue. Let's see a bit of these challenges that we are trying to solve. So the first one would be realism. We want to make doctor-patient conversations that are realistic. And how do we do that? First of all, can the foundation models get realism? Can we get them to act as humans? Or are they too narrowed by the training data on which they have been built? The other thing is, can we enforce a certain scenario? Can we enforce these models to make it a doctor-patient conversation and not just any conversation? And in which aspects do we care about the authenticity of this conversation? Like, do we want to ensure that it has linguistic features that resemble those of the real conversations, like turn lengths or turn amount of turns? Do we look at the consistency? Is the patient always the same patient? Do we look at the flow of the conversation? Do we look at the clinical exchanges? Are they like the ones that a medical doctor would have? And we can also look at the audio, like the posture of the patient. Does it change the way of speaking? Does the emotions change the way of speaking? Can we make it sound like a real patient? And are there other sounds that we would like to encode in it and that would make a change in the realism of these conversations? Of course, the acoustic environment as well. And there's many of these open questions that we have set ourselves to solve during the workshop. In terms of diversity, we could make a really, really good conversation, but it might be the only one we can make. So this is not what we want. We want to cover the variety of real conversations. And here's where we ask ourselves, can we sample from LLMs? Is it something we want to do? If not, what can we do? Do we want to match the real world distributions of behaviors of conversations, or only care of the coverage? And if we generate personas and we use them to drive the LLM, how does the stochasticity of the context affect the output results of the dialogues? Finally, about controllability. If you have worked with LLMs, you know how difficult it is to control them, to get them to do what you want to do. And here we looked at two basic approaches. One is prompt engineering, which is very helpful because we don't need to retrain these systems, but it's also a bit unpredictable of what the results we will obtain. And we also looked at activation engineering. So looking at opening this box of the LLM, of course, is much more hard to do. We need a lot more engineering work, and it has been shown to work in very controlled situations. So we want to approach this persona-based dialogue generation from this point of view as well. And finally, how do we evaluate if a dialogue is good or bad? So here, we want to see how to measure the success of such a complex task and how to do it without reference data. Finally, can we automate these evaluations instead of the human having to read all of them? And if we automate them, can we use that automation to improve our generation? So how do we do this? I'll just name a few of the key papers that we followed or that we saw were related, like the Speech Dialogue Factory. They also do the same thing with personas, but not in the context of doctor-patient dialogues. We have the self-taught evaluator, which we try to use an LLM that we fine-tune with synthetic data to avoid the need of human annotations. We looked at index TTS as a way to synthesize speech with more stylistic manipulation, so changing the way it speaks. And we also looked at refusal in language models, which is the case in which a language model refuses a potentially harmful request of a user, and they see that we can intervene in the activation space to elicit or to inhibit this behavior. This is what we have taken as reference. And finally, what have we done? During this month, we have been able to improve the diversity and the realism of these doctor-patient conversations by using persona definitions. We have done human with actual physicians evaluations and automatic evaluations of these generated dialogues, and we have been able to create an audio synthesis generation pipeline to have much more natural speech of these dialogues. Finally, we have also looked at some methods to do the activation space engineering in order to try to control these dialogues in a better way. So as for the outcomes, the SDialog library is it's a library, a Python toolkit. Actually, this one was started in this JSALT. So it's true that it uses the other one, the dialogue flow that was in the previous one, but this is a prize we can take. Thank you, Sergio, for that. And the data set that it's in the works, 20K dialogues, with 200 of them being synthesized with audio, and we will try to put them under a permissive license. So this is the outline we're gonna follow. I'm going to give the word now to Thomas, who will cover the doctor-patient dialogue and generation evaluation. And little by little, we will work through all these blocks of audio synthesis, interpretability, and analysis, and we will end with a nice demo of his dialogue. So without further ado.
So there is no prompt, or so I have to wing it. Which button is to the right? Okay, there's no, okay. I have to wing this a little bit. I had some notes. Okay, so you might ask, what is the goal of synthetic data generation? And if you have a clear defined downstream task, it's obvious you want to optimize the performance on this task if you have a metric for this. But our team actually aims for something more radical, I would say, in the sense that we want to generate conversations between doctor and patients that are generally useful without having a specific downstream task in mind. And for this, actually, during the workshop, we worked together on a set of open source tools, namely the SDialog, which was really a great foundation for doing all these experiments that we did. So what is the goal of synthetic doctor-patient generation here? What makes it a good conversation, which is we want to have good properties in the sense that we can have all the challenges of a real data set. And the goal here really is to make something that is useful generally for many different tasks. To do this, we want to aim at systems that actually Emma is working on to support end-to-end modeling of speech understanding systems, not just speech recognition systems or speaker diarization. So one of the applications, of course, is to train these end-to-end systems, but also we want to help enable models that are developed for clinical tasks, like assisting, as Ricard mentioned, training of new medical students, or assessing actually errors that happen in conversations, and to have a So all of these things share some structure in the sense that they are having the properties that are best served if you make most realistic conversations, right? So if you don't have a specific task, realism is key. We also want to avoid some of the bad properties of real data, which is, for example, in the healthcare domain, it's super difficult to get access to real doctor-patient conversations. Most of them are, if you have access to some of the conversations, they are simulated. Mock conversations, they are very limited. One data set, for example, is Brno 57, and the 57 actually means how many recordings there are. 57, you can see it's not a large number. And actually, Ricard, you mentioned the 200. We want to actually release 20,000 or even more recordings in the end, right? So, in addition, we wanted to make sure that these recordings and dialogues that we release have permissible licenses so that they can be used for all sorts of tasks, including, for example, creating new annotations, and foster research in academia and industry in this domain. And here, the last thing actually is we also want to have synthetic data that is, and this sounds a little bit like George Orwell's 1984, where good audio, in this case, is bad audio. And you will hear a lot more about this later. Okay, so what makes it actually useful for downstream tasks? This is actually a finding from the data research, which, thank you so much. So we will operate under the assumption that a lot of these different models that are used for downstream tasks use similar architectures for machine learning or deep learning, which also allows us to make the assumption that they have similar generalizability qualities or properties. And one key finding from the data quality studies is that if you have one example that is challenging in your test set, but you have one that is close to it in the training set, then your performance on these examples is a lot better, something that probably a lot of people have observed empirically. And therefore, our goal is to ensure that we actually have not only a good coverage of the center of the distribution, but also the broad distribution covered. And we do not have to actually represent the proper distribution of the data. We can recreate this through stratified sampling afterward. One big advantage here of synthetic data generation also is to simplify the label generation that you do. Oh, now I have to juggle two, yeah. Thank you. Okay, so the question, of course, is what is difficult between these, what is difficult for one task is not difficult necessarily for another task. So, for example, if you have a very easy-going conversation between a doctor and a patient to do something. It could be super easy to understand, but at the same time, if the microphone is placed not well, or if there's accent involved, or machinery that makes noises, speech recognition, diarization, and all of these things can be very bad, and therefore making the task very challenging. In the same way, if you have very good speech recognition of a conversation, it is a complicated, convoluted conversation with going forward and backward, with hypotheticals. It could be very challenging to identify whether the right medication order was actually done. This is a challenging task too. Okay, so this is about generating labels, and I probably rush a little bit through it because we have a lot of things to cover. It's obvious if you start with the text, it's easy to generate labels for the ASR and for the diarization. It's really direct. For other tasks, it's also easier to work with text often to generate the labels because you don't have to deal with all the errors that might come from the audio processing. And because of our permissive licenses, we hope that others might actually generate human labels for smaller subsets or for maybe even the whole data set to challenging tasks, for example, clinical annotations that then can be shared among the research community to drive the innovation in that area. Okay, so, so this is basically, so our synthetic dialogues are designed to be useful by being realistic, and we are driving this by aiming for 3 key qualities. One is difficulty, to cover the space. Diversity, as Ricard said, it's not good to have a realistic, but always the same. And then, of course, realism on many, many different levels, like how they interact and so on, turn-taking. And therefore, we have the linguistic challenges, and we want to actually generate challenges that are real, data that is challenging for current technology. So one of the motivations of this is to have data that is difficult to process for current end-to-end systems to create speech understanding. So speech recognition end-to-end systems, we heard that there is already some work on that tries to understand some aspects of the audio that you will hear later, but I think tomorrow from the Augie team, and today you will hear from the Emma team that also works on similar problems to advance the technology here. To achieve this diversity, you will need to innovate in the sense how to sample and create these personas, and you will hear more about this from Andrew in a moment. And then one of the things that decisions that we opted for was actually to avoid information leakage, and therefore we used a multi-LLM approach for the dialogues, which has some pricing effects between the agents. So there are quite dialogue-y, I would say. Okay, so this is an evaluation preview, and I will keep this ultra short, so maybe, oops, thank you. 2 tasks at once, right? So a crucial question, of course, is how good are we, and therefore you need an evaluation. And the evaluation usually comes first, which was actually developed here in parallel. The main goal initially was to match certain distributions from real data. So this is the linguistic evaluation aspects here. How do these speak? Do they speak like real humans? How's the turn taking? Then, of course, the question is, are these conversations challenging? So we have actually humans and LLM as judges to assess this. So this is work that will be presented in a moment. And then, as mentioned before, one very important aspect is, and that's actually a really important aspect, if you use personas, you will want to make sure that the conversation adheres to the persona, and that needs some investigation of the controllability, and we made some advances there too. So on that note, I move on and hand over to Andrew, who will, oops, the other one, who will provide some information about different design decisions we made in building the system and how they affected the output. And then Amy, Tomirs, David, and Haas will talk about the evaluation aspects of the dialogue generation.
So I think Ricard is going to try to switch us over to a different presentation system, but I'll get started while he does that. This is falling apart. So I'm going to start with two important design questions for the generation system. First, what input should it receive? And second, first, what input should it receive? So particular area of discussion here was, should we rely on LLMs to generate inputs? Stuff like information about the doctor, the patient, the reason for visit, or should we rely on some external sampler to do so? And second, what kind of structure should be used for generation? So here the focus was, should we use a single LLM, multiple LLMs? There's some hypotheses here about information leakage that Thomas mentioned. So are we actually live this way? Okay, cool, great. Okay, looks like we're good here. So meta questions are, what hypotheses did we have about these design questions going in, and what did we learn through our experimentation process? I guess I'll use, can you just use the keyboard? I mean, oh, no, now it's working. Okay, good. So let's start with a warm-up question. Immediately pressing all the wrong buttons. So the absolute simplest system you could build for this task is just prompting an LLM to generate a dialogue between a doctor and a patient. So I gave this question to Gemma 3, 27 billion 4 times with the default sampling parameters, so temperature of 1. And I'm going to ask you some questions about the outputs. So these are all questions of the form, what property did all 4 of the generations have? And these are going to be increasing order of specificity. So let's start with the race of the doctor. So here, who here thinks that the doctor always had the same race across all 4 of the generations? So raise your hand if you think the doctor had the same race. Does anyone want to speculate as to what that race might have been? Black? Okay. Are there speculations? Asian? Okay. My team already knows the answer to this, so I don't know why they're participating. Let's get more specific. Will the patient always have the same complaint? So who thinks the patient will always have the same reason they're visiting the doctor? And even more specific than that, will the doctor always have the same name? So raise your hand if you think the doctor will always have the same name. The team continues to cheat at this very easy to cheat at task. And most specific at all, the dialogue will open with the line, hi patient name, so you fill in the patient name there. Good to see you, so you something. Raise your hand if you think this is the case. Okay. So here's the start of the 4 generations. The answer to all 4 of these questions is yes. So if you answered yes to these, you have a good understanding of the output diversity of current open weight LLMs. If you look in a little bit more detail, the dialogues are extremely similar. The doctor always has the same name, Anya Sharma. She's Indian. The patient is Sarah Miller half the time, she's 32, and Liam Miller the other half the time, who is in his early 40s. They're all experiencing the same symptoms, feeling tired. This is a toy experiment using the chat model. We ran this using our final pipeline at the end, and the result is out of 2,800 dialogues, there's 3 different doctor-patient pairs. So you kind of get 3 conversations. So out of our 3 goals of difficulty, realism, and diversity, we can immediately tell that diversity is going to be a problem. This was a surprise. The extent of this weakness was a surprise to many of us. We hoped that we could use LLMs as a sampler for hard-to-sample things, but essentially we found this doesn't work very well. The situation is more like the picture here on the right. If you think of Y as the generation and X as the prompt, here the cartoon prompt is generate a conversation between a doctor and a patient, we can see that subsequent samples from the LLM tend to be very similar to each other. Here the real distribution is pretty wide, but the LLM just picks this band, which it hits again and again. It's kind of a quixotic band, but that seems to be what's happening. This was disappointing, and developing a method to achieve output diversity was a key objective for the first part of our work. So we had a million ideas for how to do this, and we focused on personas. So these are brief descriptions of the doctor and patient. The idea is we sample attributes from some external sampler, which we build, and we condition the generation on these attributes. So instead of saying a doctor in the prompt, we'll say Pinky Batara, age 59, Mongolian, and she has this kind of personality. So you can think of this conceptually as instead of drawing samples from Y conditioned on X, we introduce some auxiliary variable Z, the persona, which we can control the sampling distribution for. And then we sample Y conditioned on both X, this should be a dialogue between a doctor and a patient, and Z, here's the information about the characters in the dialogue. And what we end up with is the picture on the right. So the output diversity problem is still present for a particular prompt persona pair, but because we have a huge number of personas, we get diversity across this distribution now. So there are clear advantages of this approach, as long as the LLM is controllable with respect to the persona attributes. So as we change the inputs, we get different outputs. We're going to get output diversity. We don't need to train or fine-tune an LLM to make this work, which allows us to do quick iteration. The generation is quite interpretable. So if we change an attribute, we often know how we expect the output to change, and we can check for it. If we see some distribution where we have less diversity than we want, we can just add another attribute to the sampler. Also comes with some limitations. It doesn't fix this underlying issue with the LLM. We get the same output for the same persona prompt pair. And anything we don't specify has no diversity. So if this manifests in some funny ways, for instance, all the helper people in the dialogue, like the nurses and assistants, are all just named Sarah every time, right? There's some computational cost to this. We have to add additional input tokens to the generator. It doesn't matter much for our application. It can matter for some others. And we have to actually build this persona sampler manually. So here we hit the standard modeling problems. We have to find data supporting the distributions we want to sample from. It can be hard if we want to match real distributions. And we can run into internally inconsistent samples. So an example here is maybe this part of the real distribution that has very little probability mass is where we have a 90-year-old seeking clearance for active duty military service, right? We can try to minimize these contradictions when we're building the sampler, which we refer to as making the attributes orthogonal, or we can try to filter them out using, say, an LLM as a judge. This is a tricky enterprise because you can come up with a story for almost any combination. Maybe this is a delusional 90-year-old who really does come to the doctor's office saying this. So let me briefly describe the personas we use and why. First, we're planning to use somewhat weaker open and weight models, so we have permissive licenses. So we hypothesized that using simpler personas would be better. So we focused on attributes that are impactful. They should either affect the linguistic or the clinical content of the dialogue, or both. We also need to sample these things externally, so we thought about how easy it would be to draw samples from different attributes. And we try to avoid conflicts, personalities that just don't make sense intuitively. We also found that we need to avoid bad surprises. So we discovered in an early version of the generator that the doctor realized the patient was a child like halfway through the conversation because it wasn't part of the doctor's input. This is unrealistic. And by including these in the persona and then passing them to the other agents in the dialogue, we can avoid this problem. So here's the persona for the patient that we ended up with. So all these attributes are sampled uniformly from predefined lists. It has some basic info about the patient, name, age, race, gender, insurance, height, and weight. This is mostly, it's needed for realism. The doctor would know these things, but they also have substantial clinical impact. So they create some clinical diversity. We also have this very simple personality model with 4 traits: forgetfulness, formality, hurriedness, and openness. These were informed by talking to clinicians about how they perceive the personalities of their patients. If you don't give traits, especially with negative values, the doctors and the patients are very perfect, and there's no friction in the conversations. We also include a language attribute. This should strongly influence the linguistic features, but it doesn't work that well with Gemma 3. If you say someone has basic English, Gemma 3 doesn't really know what to do with that. We also include some additional features for more linguistic and clinical diversity. The most impactful of these is the reason for visit feature, which causes the dialogue to take completely different paths. So this is our patient persona. The doctor persona is almost the same. So we use the same personality traits for simplicity. We remove the patient-specific stuff, and we add a years of experience attribute, which our clinicians told us would be really impactful for how the doctors practice. So let me tell you about the different methods we used for turning these personas into dialogues. So in bold is the name we'll use for the method in the result slides that are coming up. So across these methods, we keep the prompt as similar as possible. So this is really trying to do science on the method's impact. The idea is we can study the generation methods and make conclusions about what is helpful for different goals. So we start with single agent methods. The absolute simplest one here is just create an in-person spoken consultation between a doctor and a patient. So single LLM, no personas. We bring in our personas by adding between the doctor and the patient described below to the prompt. And we had several hypotheses about the single agent setting. First, we thought, well, I showed you this early diversity experiment. Without personas, you get no diversity. You should see this in the outputs. We also thought that a single LLM might produce dialogues that are too smooth, right? The doctor can see the attributes of the patient, so it knows what questions it needs to ask and what the answers will be before it asks the questions. We also thought that the LLM language would be more like written than spoken language. The vast majority of pre-training for these models is based on written text. We experimented with multi-agent generation with hypotheses that it prevents information leakage, and maybe it improves controllability because the model has a more cleanly defined task. So here we have one LLM playing the doctor and another playing the patient. So the doctor's prompt would be something like, you are the person described below conducting a in-person spoken medical consultation. We also experimented with few-shot prompting here. So we give some examples from real reference dialogues as part of the prompt, and we see what changes, right? So maybe this leads to more natural dialogues linguistically because they're closer to the reference, but also could cause some unwanted persona leakage from the references and reduce controllability. We also tested multi-agent generation without a persona to try to clarify the differences between single and multi-agent generation. Okay, so I'm going to hand things over to some other team members for evaluation. So first, Amy will present on the first 4 points. First of these, do the characters talk like our references? Important for realism. Are the dialogues diverse? If we're going to generate 20,000 dialogues, there better be lots of unique things happening. Are they medically and interpersonally challenging? If we want to use these to train clinical systems, we need difficult examples. And are the doctors and patients believable to clinicians, right? Also realism. And then Tamiris will be talking about controllability. Are the doctors and patients consistent with their personas? And last, our subject matter expert, Haas, will be talking about how the doctors perform clinically, very important for realism and training. I think you're, just press.
Thank you, Andrew. So I will focus on 2 measures to evaluate whether the characters talk like humans. We calculated turn length and the Gonic Fog Index for both doctor and the patient. Turn length is just the number of words per turn. For language complexity, we will look at Gunning-Vogt. It is readability score that is commonly used to distinguish LLM outputs from human outputs. So it just counts the average number of words per sentence and the fraction of 3 or more syllable words, weighs them and adds them together. First, I will talk about the turn length. The doctor graph is on the left and the patient graphs on the right. The x-axis shows the different generation methods with the multi-agents models in blue, single agents in green, the references in red. The y-axis shows the average turn length, and the error bar shows the standard deviation on a 2,800 dialogues. There are three key takeaways. We see that multi-agent methods generate consistently longer turns, and the references themselves show substantial variation in turn lengths. So looking at the two bars on the left, fuchsia prompting has some effect, but it wasn't very strong. Here we see the multi-agent methods results in more complex language. We hypothesize that multi-agent methods have longer turns and more complex language because they are post-trained based on the human preference who prefer this. And the effect is less in the single agent methods where the generation is already very long. We can see the persona decreased language complexity in both the doctor and the patient and in single and multi-agent generation. Also, fuchsia prompting has limited effect here. We experimented with truncating doctor turns after the first question mark. We saw doctor turns like this, where the doctor would ask a question, the patient would need to answer, and then not to wait for the patient to respond. Instead, continuing with another question. So as you can see here, do you have any known allergies to medication or anything else, Gabriel? And have you noticed any other symptoms like fatigue, weight loss, or changes in your appetite? We observed the doctors now waiting for the patient to respond. We found this unrealistic and implemented a rule that the doctor should pass in turn after a question mark. We use this rule in all the multi-agent generation methods. Truncating after the question mark reduces the doctor turn length by 20%. We didn't do this on the patient side because many patients, we didn't do this on the patient side because many patient questions are rhetorical, leading to unnatural turns after truncation. This is a Gibbs law plot. It looks at the number of unique words at each frequency in the data set. The rank appears on the x-axis, and the count of words at the frequency rank appears on the y-axis. So the lower and lefter means less lexically diverse. We see that multi-agent dialogues with personas are the most diverse. Fuchsia reduces diversity slightly here, and we see that removing personas heavily reduces diversity. We also see that single-agent generation symptoms produce less diverse outputs than multi-agent ones. In frequency analysis of human text, the least frequent words always have one appearance. In the single agent no persona ablation generation, the least frequent words has 900 appearance here. Next, let's look at ratings of medical challenges on the left and the interpersonal challenges on the right. Here, the x-axis shows the score, where the 5 score is the most challenging, and the y-axis shows the frequency of that score using Sonnet 4 as a rater. We see variety over both types of challenging scores. We experimented with using different variants of anthropic models as raters, including opus with and without thinking. Qualitatively, results were very, very similar. So we report only SONET 4 scores in the following slides. We also had 3 clinician rated the dialogues on various measures. For these challenges score, agreement between the clinician and SONET 4 was okay, especially for medical challenges. Here you see the Gryffindor's alpha of around 0.6 for medical challenges and around 0.3 for interpersonal challenges. Just a caveat, these are small samples of dialogues. Here we compare the average challenges scores of dialogues generated by different methods. We see the persona increase challenges scores in both single and multi-agent generations. We also see that multi-agent generation leads to higher interpersonal challenges score when personas are present, supporting our hypothesis that it makes conversation flow less smoothly. SONET 4 scored the doctor and patient high for believability here, but there was low agreement even between LLM raters on the question. The audition of the persona decreased the doctor believability. This is because the less open doctors were rated as believable by LLMs. For clinicians, we also found little agreement on which doctor or patients are believable, with Gryffindor's alpha of around 0.2 for doctors and around 0 for patients. Next, we evaluated persona adherence using LLM as just, assigning scores from 1 to 5, where 5 indicates high adherence. We also conducted a human evaluation alongside this. Here, the SONET 4 ratings with doctors on the left, the patient on the right. We found that the multi-agent generation approach achieves higher adherence, which we hypothesize is because each agent only needs to focus on a specific persona, which makes it easier to stay consistent. Our hypothesis that fusion prompting would cause personality leakage was validated. With fusion prompting achieving 10% lower adherence rating for the doctor and 15% lower for the patient. There is an interesting observation here we can make in the no persona ablation. In these cases, the generator did not receive access to the persona. So the persona is essentially random. We see that the doctor gets an average adherence rating of around 2.5, but the patient receives a lower score, 2.0 or less. This suggests the patient role is harder to perform well. Essentially, the doctors get some adherence points just for being a doctor. We conducted a human evaluation of LLM adherence judgment using non-clinical evaluators and found a Gryffindor's alpha of around 0.36 for the doctor and 0.1 for the patient. Next, Tomiris is presenting her work on a self-taught evaluator.
Hi. So our team also performed evaluation on persona adherence. Our goal was to build a self-trained evaluator to see whether a model can maintain a consistent persona within a dialogue. And the reason we're doing this is because we want to control our generation. But the problem is that we actually don't have high-quality preference data to train our model. And using state-of-the-art closed models is very costly and also non-reproducible, whereas using human annotation is also costly and time-consuming. So our approach was inspired by the self-taught evaluator paper, and we're going to be doing iterative self-training of small open-source models on contrastive synthetic data without human annotation. To give an overview of our approach, we start by generating personas, which are minimally different from one another. And then we generate dialogues, and for each dialogue utterance, we score it against the matched persona and then the unmatched persona. And in such manner, we create a contrastive training set that we then use to train our model. And we iterate through the steps as many times as needed. And I'll go over each step in more detail. But first, I'll briefly outline how our approach is different from the original paper. So their approach relies on an already strong model of 70 billion parameters. But we are actually trying to use smaller models. And additionally, we are also experimenting not just with pure self-training, but also incorporating knowledge distillation. The persona adherence task is actually difficult, and it's kind of underexplored. And the way we construct our training examples is more controlled as we perturb persona traits. And finally, our approach can also be applied to multi-turn dialogue context. To start, we're using as dialogue one of the main contributions of our team. We generate personas. So we set one attribute to a different value. So from formal, in this example, we set it to casual. So we generate a lot of these patient and doctor personas, and then we create dialogues between them using open source models like Llama 70 billion and Gemma 27 billion. And we specifically focus on personality attributes that our team defined to be orthogonal. And these are formality, hardness, openness, and forgetfulness. So once we have the generated dialogues, for each dialogue utterance, we scored against the matched persona and the unmatched persona. And if the score for the matched persona is high and the score for the unmatched persona is low, we say that this utterance reflects the attribute. And the reason we're doing this kind of data selection is because not all utterances actually reflect attributes, but this logic ensures that we actually select contrastive examples. And so this is how our training data looks like. We have an utterance that sounds formal. So against the formal persona, it gets a high score of 5. And against the unmatched persona, it gets a low score of 1. And so this is an example of this is a contrastive example that we use to train our model. And this is how our training scheme looks like. Once we have the data ready, we fine-tune our evaluator via DPO, and then we use the fine-tuned evaluator to rescore new data, and we can iterate through that process as many times as needed to improve it. And to measure whether our model actually improves, we created a test set. We randomly selected 65 utterances paired with personas, and we asked 3 raters to label them manually. And the initial agreement was 0.4. So we then applied majority voting, and we removed utterances where all 3 raters disagreed. So the new agreement was almost 0.6, and the resultant test set was well balanced across the attributes. And David will now speak about the interface that we used for our human evaluation.
So on the right, you can see a persona evaluation interface that I created using React. It is designed to be quick and easy to use and very snappy, because once you submit, it will automatically give you another utterance without reloading, because I add that part in to make sure that there wouldn't be problems. Also, it can switch between either a single utterance or the entire dialogue. And lastly, all results are saved to a Google Sheets.
So we've only been able to do 1 training iteration so far, and this is the optimal beta for that. We tried quite a few different small models, and these are the ones that performed best. So the metrics we're focusing on here are the score match percentage, which means the model predicted the same score as the raters, and the category match percentage, meaning the model predicted the same category. And we also looked at probabilities to see whether the model is getting more confident in predicting the goal scores and categories. And we can see that after training, all 4 metrics improved for both models. And in fact, for both of the models, in category match percentage and the probability, both 3 billion llama and 8 billion llama have outperformed the 70 billion llama, which is like promising to us. But also you can see that even among the bigger closed models, like the 70 billion llama and the Claude in this case, the performance on this task varies greatly. which suggests that this task is actually difficult, and we also need to compare it to other closed models and improve our human evaluation. To conclude, control generation is possible without using huge models and without using human annotation, and our evaluator can be used to identify utterances for steering, which is something that our interpretability team will share later. And I'll not go over all the next steps, but we're planning to do more training iterations and incorporate more knowledge distillation, improve our human evaluation, and also compare it to other state-of-the-art closed models. Next we have Haas. Yep.
Yeah, it's a sort of a quick question. It's curiosity-driven, and actually it's a question for Amy. So Amy, if you're still here. Yeah, can you come down? So it was triggered by Tomiris's talk, but I was thinking about the lexical, like, you know, you have the index which measures complexity and so on. You were generally trying to match the mock dialogues and trying to see if they're similar, but you didn't say much about how things like turn-taking, turn lengths or vocabulary usage changes with attributes in the persona. So for example, should I expect that patients who are supposedly suffering from depression should have shorter turns, or neurotic ones longer, or should highly educated patients be using more sophisticated vocabulary? Do you have any evidence? Have you started looking at it? I mean, it connects it to sort of back, because it would then fall into this adherence to persona type of questions. Just a quick comment. We can have a longer discussion later, but yeah.
I'll give the quick comment that we did look at some correlations for personality traits. There are results. We haven't fully processed them. Some of the interesting ones, the nicer doctors take longer turns. The longer turn doctors get rated higher on like every axis. We haven't looked at the trait or the reason for visit correlations, because there's 1,000 reasons for visits. So to get sample size, you actually need a lot of dialogues.
Thanks. Yeah. By the way, I'm hoping questions like this are okay as you talk. And okay, all right. So the floor is open to others if you have such questions, now or later.
Okay, so why do we bother with a clinical evaluation for a synthetic dialogue? This is part of what I call facilitating responsible innovation. Specifically, what's related to our team is to inform the benchmarking and how we can improve the AI-generated dialogue, specifically from a clinical point of view. Because if we can have a really deep, factual, omission-free dialogue, we can have a diversity in tokens and factuality and a clinical authenticity. These are the core criteria to assess the clinical, would say it, clinical critical information within the dialogue. Number one is factuality. Did the AI actually did an accurate and correct information when seeing the patient? It doesn't mean completeness. It just means whether it was factual, free of misinformation, and so forth. So it's not a complete measure. You have to address also omission, which is the completeness of the clinical information. And then the safety, the impact of factuality and omission on patient safety. And then there are communication quality, ethics, and culture sensitivity, but they are patient-centric. The score that we used is 135 deliberately. That's what we use in medicine. We avoid in-between scores, so we force a signal in one direction or the other. That way we can enhance disagreement or agreement between evaluators. We had 20,000 generated dialogues, and based on a power calculation, we needed a 377 sample to be reviewed manually to get an information about the entire corpus of dialogues. The data was generated as one physician for every 200 patients, and the 200 patients were circulating across the 100 physician persona. So we did a stratified sampling within every 200 block, and that way we ensure every patient, every doctor was sampled, and the total sample was 380. The human evaluator was me. I'm a clinician at Johns Hopkins and an epidemiologist. The AI model that we end up picking for LLM as a judge was Sonnet 4, and the AI model that generated the dialogue was Gemma 327B. This is the initial results. This is the factuality. If you look at it, most of the dialogue were factual, between a 3 and 5, which is adequate to excellent. There were some instances of misinformation, which was mostly related to math. The model was not able to calculate medical math-related calculation that direct the dialogue towards one information. So this was, for example, miscalculating someone who's underweight to overweight and then direct the dialogue into the wrong direction. But if we look at the omission, which tells you the rest of the story, then most of the dialogues actually have a critical omission components. So despite that the model said what it knew, it was factual, but the rest was not there because there was an omission issue. And the omission mostly show up as the model thinking about the superficial diagnosis, not the serious diagnosis, and therefore omit the right questions, the right bedside exam, and the right test for that. For example, the model will rarely ever suspect cancer. It always resort to superficial explanation. If a patient presents with weight loss, it always think it's a thyroid. It will never think it's a cancer. Or someone was coughing for 6 months. That's a very strong alarming sign for cancer or tuberculosis or sarcoidosis. But the model thought it's just sinusitis running for 6 months, which is clinically not correct. If we look at safety, of course, that impact the safety of the patient because of the omission. So there were some instances, about 20% safety issue. The human evaluator, which was me, I had a higher rating of safety mishaps than the LLM model. In communication quality, I think this is where LLM are good at. Words is their game, so they excel well in communication quality. They're using the right word and choice to communicate with the patient. So that was not an issue. It was from adequate to excellent overwhelmingly for most of the dialogues. Professional ethics was also overwhelmingly positive in an excellent direction, except in a few instances where the patient corrected the name. They said to the doctor, no, this is not my name, this is my name. And the doctor got mad and then called them in a racial slur. That was one of the instances that was alarming. Culture sensitivity, the majority of the dialogue score 3, which is adequate because there was no active seeking of understanding the culture from the model, despite that there was a knowledge of the doctor agents, of the background of the patient. This is the overall correlation with the Spearman rank. Everything is positively correlated with each other, but we can see a strong signal between omission and factuality, between safety and omission, and communication quality and ethics. In a reverse test of clinical authenticity, this is not a language authenticity, clinical authenticity, where the hypothesis is the dialogue is clinically authentic, and the AI has to prove to us that it's not. 98% proven to be not authentic, except few. And those few, when I reviewed them, they were mostly about doctors in a hurry. They have closed-minded persona. They don't want to talk. The patient was frustrated, and they had an issue between them. And the model thought that was the most authentic clinical thing about it, which says a lot about our healthcare system. And lastly, this is the doctor performance score. As you see, the issue here is that it's very hard to get doctor to agree on a specific score. And it's very difficult to perform a clinical evaluation on a synthetic data. To give you an example is between Dr. 1, which was me, and Dr. 2, for example. Dr. 2 said, I have never seen a patient requesting medical clearance to fly. So it rates that dialogue as not realistic. But 2 weeks before the workshop, I got that request. Someone asked me for medical clearance to fly because United Health, for example, has a medical clearance requirement for certain kind of conditions. And in summary, I think the LLM as a judge is feasible, and that will help us expand the evaluation and inform data generation. Factuality is a misleading measure. It has to be paired with omission and safety to get a full picture of the clinical quality. there is a need to understand if the model had a limited clinical knowledge, or if we failed to elicit that clinical knowledge in the dialogue to address the omission issue. And finally, the limitations. It was a single physician review, which was me. It was a very tedious task. We tested only 3 frontier models, and we settled to Sonnet. It's unknown if the results is applied to real dialogues. For example, if I will train a model now to assess doctor performance, if I take it to a real dialogue, will it perform the same? That's unknown. And clinical judgment is a multimodal judgment. In a clinical practice, we look at the patient, we hear the patient, we look at the way they walk, the way they sit, the way they speak. So judging the quality of a clinical content just from the dialogue is somehow not full, it doesn't capture the full picture. Thank you very much. Yeah, coffee break.
It's time for the coffee break. Let's take a rest. Hey everyone, I hope you had a good coffee break and that you're all well awake. And we will continue our presentation now with the block of audio. I'll give the floor to Marcus. All working? Great.
All right, welcome back, and I hope you are as excited as I am to hear about the second part of our presentation. So in the first part, we basically discussed how we are going to generate these dialogues from a text point of view, but in order to achieve what we set out to do, we of course also need to have the audio synthesis to create really doctor-patient conversations. And the big question is, of course, I just want to reiterate this, so why do we need to have the audio part? Well, our goal is to enable the development, training, and evaluation of speech technology, and for this you really need high quality, in our case synthetic dialogue data, to enable this. And I guess this is also a theme which is linked to other teams here at this workshop who rely on such kind of a data. And as you probably all know, in the speech domain, you really need to nail the acoustic conditions in order for good system performance. Now, I said high quality data, and what I mean by high quality data may be low quality for some people, and I just want to play you a very quick snippet of what quality we're aiming for. So this is a real recording that you're going to hear. Yeah, so you heard it's very noisy, has a lot of artifacts in it, and because these are doctor-patient conversations, as you probably can see in the picture here, it's almost impossible to collect these in real life, because imagine you were going to see a physician and they point a microphone at you. That probably would not go well. So what are the challenges that we're facing here? Similar as on the text side, we also need to make sure that we match things in difficulty, variety, and realisticness. So we want to have authentic voices, authentic background noises. We need to have some time alignment, as we will hear. And of course, we need to match the acoustic conditions. Also, part of as dialogue, we want to make this very easily reproducible. And also, we want to ensure the integrity of what we are generating, meaning we want to make sure that we get the right, for instance, SNR or room acoustics. So where did we start? We start with looking at what are the limitations of the existing systems. So when you think of TTS systems, usually what you think about, those systems generate very high quality dialogue, meaning professional speaker, close talking microphone, and a very professional recording environment, which is a little bit completely the opposite of what we want. So our realistic dialogues actually suffer from intelligibility, because we want to have all these distortions like room acoustics and so on. At the same time, because we are talking about doctor-patient dialogues, it's not just the speech, it's also more like the audio that we also need to generate. So for instance, doctors typically typing on a keyboard. And while that may sound the same, it's kind of the same, but always different. Yeah, the typing sound is always different. So we are also looking into, could this be something to extend from TTS to TT audio, basically to also synthesize additional sounds. And of course, our synthetic data should recreate the real life across multiple dimensions, yeah, speaking style, turn-taking, and ambient realism. And how we do this, we're going to lay out in this block. And I hand the microphone over to Yang, who will discuss about the TTS.
Thank you, Marcus. So the first problem we want to address is how to generate audios with good prosody. The simplest way is to just use plain text as prompt, but the prosody is very limited, and the controllability is also very limited, and so we can add some description. So we can diverse the prosody, but the output is hard to control. So finally, we found zero-shot TTS with a text and an audio as prompt. We can generate good audio with highly diversities in prosody, and we can control it very easily. So we tried many zero-shot TTS. First, we found 11 labs. The output is quite impressive, but the price is very high, and the customization options is very limited. So we turned to find open source zero-shot TTS. Finally, we found index TTS 1.5. We can hear how it sounds.
All right, 44 years old, let's get started. All right, 44 years old, let's get started. Tell me what brings you in today, and try to be concise, please. I have other patients waiting.
So you can hear that the output of the index TTS 1.5 is quite impressive. So we decided to use that model as the beginning of our pipeline. And moreover, it's free and it's open weight and style controllable, so it's very good. Okay, now we have a good TTS model, and we have text that we want to turn to audio. The only missing piece is how to find a good audio prompt to match the speaker's identity and emotion. The problem is, everyone will interpret the emotion perceived in the same audio clips differently. So how can we match the emotion accurately from text to audio? The answer is we can quantify the emotion by VAD emotional model. In our context, we means valence, which means how pleasant or unpleasant an emotion is. And arousal means the level of intensity or activation of the emotion. And dominance means how much control one feels over the situation. As text and audio shares the same criteria under the same VAD emotional model, we can easily map the text to audio correctly. Okay, now we have all the elements we need. Now let me walk you through how our system works. Okay, so first we have a dialogue that we want to generate to audio. First, we use LLM to judge the valence and arousal dimension from this text. Like here, we have 4 and 4, the number of pair, and we will search in our audio database to find the audio with the exact same valence and arousal number. So we found speaker C, and then we will use this speaker C as audio prompt to generate our audios.
Okay, so now what we have is a prompt that hopefully matches the persona that we have created from the dialogues that was explained earlier, and it could be any persona, and hopefully we have a database of speakers that would match one of the personas that we are interested in. So we have an audio, which is, the prompt is usually around 5 to 10 seconds. It could be longer, but the TTS engine likes shorter prompts to be sustainable. So we could easily generate one turn of the dialogue, but we also want to generate multiple turns to have a conversation. And ideally, we don't want to go searching for a different prompt every time. We want the same speaker. We want styles more or less to be consistent, but not to be monotonous throughout the audio. So that's why we go for another step where we try to look to see if we could modify the prompt in place based on what we have already selected. And of course, we could imagine multiple ways to do it. One of the ways we tried here is based on taking inspiration from another paper called EmoNob, where they showed that we could adjust the emotions of the TTS a little bit here and there. And so the idea here is again shown at the top. So if we could have a sort of a knob so that, you know, the emotions don't jump abruptly across the conversation, we don't have to keep searching for the prompts, and also use the existing prompt to just make a small perturbation of this prompt to generate each and every turn of the audio that we want to eventually generate. Here I show a small experiment that I did. I have many variants of this, but what was impressive is that different perturbations and combinations of the same prompt worked pretty consistently, and the TTS was quite robust to generate variations of the same speaker with slightly different styles. So that, you know, for example, along the conversation, suddenly when the patient is complaining of chest pain, the doctor doesn't turn happy, for example. So it's just a modification of the existing prompt, but still keeping the same voice. And what was impressive was that TTS was quite robust throughout all these manipulations. So to summarize the outcomes, what Yi Yang talked about, the first outcome was that we could use LLM as a judge to reasonably pick an audio based on just the dialogue and matching the voice. Of course, we wanted to go beyond this, but during the workshop, we managed to do this. And manipulation of the style embeddings was quite robust. What I found was the linear manipulations were pretty good, and beyond a certain, you could go with the same prompt with the same voice, slightly different styles for different utterances. You can even manipulate the voice and make them sound cartoonish, for example, one of the examples where I found interesting. And so that was possible to be manipulated. And of course, there are other ways of manipulating, like I mentioned, I worked on many different manipulations, and all of them work quite robustly, keeping the style and the voice more or less as we wanted it to do. So the next step, of course, we could generate the turns in isolation, but we also want to make sure that each turn that was generated with the synthesis is consistent and makes sense for a conversation. So what the next step would be to even have some level of context awareness when generating the TTS. We, of course, experimented, as Yang mentioned, with dialogue generators, but the style and the voice quality was not really satisfactory for us, so that's why it's been interesting to work further on this part. So that was about TTS. So next, now we go to Yanis, who would be explaining about the audio pipeline.
Thank you. So for the audio pipeline, we have multiple modules. So our generation pipeline is composed of 4 modules. We start by the synthesization module, which is doing the TTS part and also adding the audio events. We continue by the model Discaper, which is working with timeline, creating timeline between the background event, foreground event, and all the annotation we have about the audio. And the last one is D-render, which is the room acoustic for the whole timeline, basically. And from all of this, we do the evaluation. So for the synthesization pipeline, it is part of the S-Dialog also. We start by using dialogue from S-Dialog. So we take dialogue with turns and persona. And with this persona, we try to match based on voice database. So we start with a closed voice database with all the information, but for the purpose of this presentation, we use only open source data to use as a database of voice for the grounding with the persona. So when we have persona attributed, a voice attributed to persona, we use index.ts to generate the references for each of the turn of the dialogue. When we have this dialogue, which is synthesized into inferences, we add audio events, noise level, timing, and speaker position using different LLMs. So we do a new pass on the text and align this text with the audio using a whisper model. So when we have all of this, we have the timeline, and we use this keeper to create channel for each of the speaker position. And with this channel, we are generating, after that, the room acoustic. So for adding the information, like I said, we use different LLMs. So for these LLMs, we are simply asking to add XLM tags with the name of the sound event, the duration of the sound event, and if we overlap or not. And we do the same for the SNR and for all other like speaker position and so on. And for this keeper, so I will let Pavel speak on this one.
Yes, we knew that we need to balance the amount of background noise and the foreground noise. So with the additional information that we generated with LLM, we set it up some algorithm to match it, because that's balanced the sound. What you heard before, what Marcus was playing, was having the door knocking, the steps, some paperwork on the table, and also air conditioning that was heavy working somewhere else. And this is a Swiss room. Some rooms are very different. Some are more fixed. With this keeper, we level up all the timeline and the events on that, align them, and match them accordingly to the setup that was provided, but also to fix some of the acoustic part of it. So we can have right now multi-channel recordings together with the mix itself. And in order to, so we have everything like in Dove set up, different channels, different audio events. Some of the audio events, we have a primary investigation to have a text-to-audio generation with various models. However, we find it that is either very bad, very, very bad, or completely out of the control. So we come up with, using library with some transformation. In order to add a acoustic part, a real simulation, we made a module called on the start derenderer, which have basically a room definition with all the acoustic properties, some of the properties of the sources and microphones and the whole setup. To get the real reality of the room acoustics, we review all the papers for acousticians and architects from various places, UK, US, European, and we found that there are typical, for US, it's for interview consultation room, it's around 8 to 9 meters squared of the floor plan, and in Europe, UK, in Australia, it's recommended to have 12 meters. That governs the whole algorithms that we could set up the room. The room can be generated. There are around right now 5 setups of the room with additional 2 bigger ones, additional doctor positions and patients, and also some other information that can be generated in order to have various situations. At the end, we call it as dialogue, and we can have a dry run after the step 2.
Hello, please come in. Have a seat. I'm Dr. Norman. What are you doing today?
and eventually have a acoustic part render. We change the microphone. However, with the already pre-generated dialogues, we eventually render 200 conversation with 6 different 3 room setups and 2 microphones, either on monitor or on ceiling. And we come up with a realistic conversation of the duration and a match of the turns. When we work, in general, patients talks more tight in terms of distributions and certain about 20 seconds. The doctor have longer passages, and in general, it takes around 24 turns per dialogue. Eventually, we have it generated, but we need to evaluate it both on various terms of acoustics and signal and speaker level.
So for evaluation, we need to see if the audio is natural or not. And also we need to be sure that we have speaker consistency during the whole dialogue. For doing this, we have 2 types of evaluation. We have the speech and the audio evaluation. What we consider in the speech, everything considered to the speaker or to the utterances. So we have speaker consistency, speaker adherence, statistic about the rhythm of the, or also the speech rate, and also basically the word rate and character rate of the transcription. For the audio, this is a bit more tricky. We are looking for the noise. If how much noise we add into the audio, is it still intelligible for speakers with the MOS, for example? And also, we are looking for quality degradation with the STOI between each of the steps of the pipeline. So for speaker consistency, we compute what we call the local and global consistency. We are looking in the local consistency between one speaker of the speaker of one for one speaker between one utterances and the second utterances of the speaker to see if between each of the utterances we have the same speaker, and we are looking also globally for the speaker if all the utterances of the speaker are coherent and are the same and consistent between all the utterances. All of this was based on a problem we found with 11 Lab V3 model, so the new one which is in alpha access. So when we generate an audio with 11 Lab, we cannot control the speaker identity. So basically, on a whole dialogue, when you can give a whole dialogue to the 3rd version of 11 Lab, and when you generate the audio, you have speaker changing during the dialogue. So each of the utterances are basically new doctor and are not the same doctor anymore. So for example, this one. So as you can see, we have totally different speakers in this case. So to prevent this, this is also why we generate utterances individually, and after that generate the sources and compute the room acoustic. So for voice consistency, we can see that most of the speakers are quite similar and have quite good consistency in the dialogue. So for the voice matching, so basically when we give a voice, do we match the voice correctly? And do we have the correct speaker attribute? So here's something very interesting. We compute the equal error rate and the Ariane curve. And as you can see, this is extremely good. So we compute the equal error rate on 2,400 speakers. And in this case, when we compare the speakers for each of the utterances with the database, we can clearly see that the voice is cloned, but not only cloned, but we have very, very good cloning, and maybe too good of a cloning. So maybe the model, the index DTS model, is taking the most important attribute of voice and replicate this attribute into each of the utterances and make the voice very distinctive from the other, which is not the case for human voices. So in terms of quality, basically the original mix of utterances is very very, very good because we only take the output of the TTS and basically concatenate everything and compute the metric on it. So this is very good quality, close to 4 in MOS, for example. But when we apply the stages for the room acoustic and for the different channel, we get a very, very bad degradation of audio, which is what we want basically. We want to simulate the room acoustic and the type of recording we have with real doctor. So when we compute the water rate and the MOS, we can see that we have very big water rate on the room acoustic. So if we take an example, so if we take earplug, earset, for example, we can clearly hear what they are saying, but here it's a bit more complicated with the type of speaker we have. But basically, for humans, this is completely intelligible. But for the model like Whisper Large V3 Turbo, which is quite a good model, we have a very high order rate of 87. So we can generate very difficult audio, maybe too difficult audio. So we need to make some audio easier to compute, easier to process for example, the ISR model. But basically, we can achieve good quality degradation, and this is what we want. So if we are looking to real data, for example, from Thomas and Adam or Primoc, we can see that the MOS, for example, is around 2.5 and 2.8 for the Niska MOS, and we achieve a Niska MOS of 1.8. So we are a little bit lower in MOS, and if we can increase the MOS a little bit, it will make it simpler, I think, for ASR model and other end-to-end model to process. So yeah, we have very bad result on this one. Yeah, this is Marcus.
Thank you. Wow, 87% word error rate. I guess you don't see that every day. But I guess that also shows that our pipeline works. We can create very challenging audio. And I guess this is something, also a little bit of a segue to the afternoon presentation, where we have a team presenting who is specifically targeting these problems. So I think this is also one very good synergy that we have with other teams, in addition to, of course, also the TTS team. So just a little bit of a quick recap here. Where are we? So now we have style adaptive TTS. We can actually control the emotion of the speaker in the TTS across these 3 different dimensions that we have here. Also, we have a great audio rendering pipeline to go from just a dry audio to really this rich audio, which has all these different noises and room acoustics in it. But we are not done yet. So we have a little bit of additional ideas what we can do. So one of the things that I already laid out in the beginning, so I think we also want to look into how can we synthesize non-speech acoustic events, like I said, typing on a keyboard, maybe opening a door, knocking on it, because if you want to have realistic data, these sounds can't be just canned recordings. You need to have a lot of variability there as well. Another thing that we did not touch on was like the turn-taking dynamics. So in a real conversation, you maybe have some back channeling or some barge-in. Right now, these conversations are, regarding this aspect, very well behaved. What we also did not look into, but what we also want to look into is things like different ways of speaking, like speech pathologies that would very well fit to like the doctor-patient use case, and also to make these room simulations a little bit more dynamic, where you have like people walking around in the room, which ultimately also alters the way how the room acoustics are reflected in the voice that we have. And with this, I hand it over to Isabella.
Before you go, Marcus, I have some questions. So, like, you know, I appreciate all the work in, like, you know, getting these controls on TTS to whatever, produce certain emotions and this and that. But in the clinical setting, don't you also want to have control over pathologies? And what is out there in the world to say how can I make this sound like somebody who's suffering a sore throat, or somebody who's depressed, or somebody who's starting to suffer from Parkinson's, or what have you?
Yeah, so I think in terms of just the pure coughing sound, I guess the 11 Labs TTS already supports this, so you can generate different types of coughing. But I guess your question was...
No, but can you do things like, I have a cold today?
Yeah, exactly. I think your question was going a little bit deeper than this, like how it is when you have a sort of, you speak maybe a little bit different or so. So I think to some extent, you can, if you have the data. I guess it's all a question about the data. So I don't think there are good data sets out there, but I would probably need to refer this to the TTS folks who may have looked into this a little bit further. But I think that's definitely an open question. In terms of general other speech pathologies like problems with speaking itself, I think there are some data sets out there, and I know some people that were unfortunately not part of our team are working on this. So this is where we also see probably some future synergies to like join forces to make the synthesis more rich with that respect.
I was wondering if the TTS team has questions for these guys.
Thank you so much for your presentation. My question is not more, it's like just about the choice that I about how to, why, maybe like why choosing controlling the text to speech or voice cloning instead of doing voice conversion for controlling more? Like it's just a question, it's not open question, it's not.
Yeah, that's a good question, and I think we also thought along these lines because you can definitely do this in a two-stage approach, but ultimately with the release of Index TTS 1.5, we found something that works well enough for us right now, but this is definitely something we also discussed because I guess that's also an interesting way to go by using like a more basic TTS system and then do the voice conversion on top of it.
So just as a remark, you probably, to get that 87% word error or whatever, you we're doing single channel stuff, right? Whereas, of course, much of the spatial or whatever the noise suppression thing is perhaps binaural or multi-channel.
Yeah, exactly. That's a good point. I mean, right now, we focused on creating a single channel, and I also let Thomas comment on this, but our pipeline is, of course, flexible enough to place the microphone wherever we want in the room, but as a starter, we just looked at what are the most probable places where nowadays one of these microphones would be placed in the actual examination room.
All right, so to situate us a bit, so before the coffee break, we saw how the dialogues are generated and evaluated, and then just now we saw how audio was synthesized from the dialogue. So now I'll be describing a little bit about the interpretability and analysis team. So as we saw in the first part, it's hard to control LLMs, and there are two different ways that we can try to control it. The first is through prompt engineering. So the reason why we introduced personas into the dialogue generation is because it helps control the LLM output. But a different way that you can do this is through activation engineering, and this is what the interpretability team focuses on. So to describe a little bit about what this actually is, so one of the main goals of interpretability is to reverse engineer models' internal components into human understandable algorithms. And one of the main goals of activation engineering is to steer the model behavior using these algorithms and using the activation space. And so our goal as the interpretability team is to use these methods to generate, investigate, and evaluate our dialogues. So what are the questions that we're looking at as a team? So one of the questions is, can we steer personas through the activation space instead of prompting? Can we analyze dialogue behavior through conjugation behavior? Can we intervene in the generation by disentangling and manipulating activations? Can we investigate how the properties in data affect learned representations? And can we evaluate whether a dialogue follows the script through the activations? And so with that, I'll pass it on to Savahan.
Thank you. All right, so let me see. Okay. So one of the main challenge of our work is how to control the flow of the dialogue, right? And it's especially the case for the agents and the persona traits related to the agents, right? So we want to see if through activation steering we can control and manipulate persona traits. But first we have to see how activation steering works when persona is involved during the dialogue. So a great way to showcase this is first to apply a good paper on activation steering, which is called the refusal direction. So the assumption is that there is a vector which involves the ability of the LLM to bypass a refusal. So to do this study, we need agents, and we need agents that have persona in it. So we involve roleplay into the persona through the system prompts, and we define two agents: a neutral agent which is tasked to roleplay his answers, and a bad agent which must act like a bad person, right? And so, a little recap on the refusal direction paper. We gather sets of harmless and harmful instructions. So here's an example of an harmful one, where we have to create a tutorial on how to hack into a secure government database, and the LLM will, of course, refuse to answer. And at the opposite, an harmless request, what are best strategies for learning a new language, learning languages, etc. So it will try to answer the prompts. So when we have these data sets, we apply each request at inference time to the LLM, and we register the residual stream. And once we're done with that, we compute the difference in mean and the output of the transformer layers, and we can generate some contrast and the vector for steering. And once we're done, we can apply this vector to ablate a direction in the activation space to alter the behavior of the LLM. So as you can see here, no persona represents the baseline from the paper. We've tested each layer and tested the refusal score on a set of harmful prompts and see if we could bypass the refusal from the LLM. We used an LLM as a judge to evaluate how good we are on the answers. As you can see, when persona is involved in the answer, it is quite difficult to steer. And we can see as well that a bad agent is easier to steer than a good one, which is a sign that system prompts and persona have an influence on this, the refusal. So here are other scoring which showcase what I just demonstrated earlier, about just more prone in answering when steering is applied, but when persona is involved, steering is much more difficult when applying the methodology from the paper. Which tells us that maybe the directions, if we analyze the content of the directions, maybe we can see that picking one direction is maybe not ideal, but maybe we can combine those directions, right? So we look at each direction and we compare each other in terms of magnitude and angle. As you can see on the left, there's a lot of dark area which assumes that each direction, the directions do not share the same similarities, and they are very different from one another. And it's the same for the magnitude. As you can see, the magnitude is not the same depending on the layer, which assumes that maybe instead of leveraging one single direction for the steering, we believe that each layer can contribute to the direction, and this is what we do for the steering. Instead of picking one layer, we pick a set of multiple layers. And as you can see here, the steering works much better and is improved on all three versions, and the roleplay agent still shows good signs of refusal, which means that there's still work to improve on that. Also, another interesting result is when we look at the in-persona score. So we ask the LLM as a judge to tell us if the answer represents a persona or follows a persona or not. And as you can see, the neutral agent and the bad agent will give a generic answer, such as, I can't fill this request. But once you apply the steering, the answer follows a roleplay, which means that bypassing the persona agents with the refusal induces roleplay back in the answer, and that also instruction-tuned models will ignore their past memory if we prompt them with those harmful requests. We can also, instead of ablating a feature, we can induce one. And this is just what we do. Instead of ablating one, we just add it. As you can see, if we take a set of harmless requests and we apply the refusal, we can allow the LLM to just refuse to answer even if the request is harmless. Which leads us to our next work regarding persona steering for dialogue flow control. So we want to generate a direction, not for refusal, but for persona traits. So how we do this, we use SDialog to generate 1,000 dialogues using 30 persona cards. And we have 2 scenarios for each dialogue, one normal flow scenario and one where we apply the orchestration system, which means that we prompt the LLM to behave in a certain way, like say is angry. And from this contrast, we can establish a direction matrix just like for the refusal. And we can analyze this direction matrix. So to analyze the content of these directions, we can project each direction vector to the output dictionary of the LLM, and we can see the output logits of the most probable tokens that the LLM will output for each direction. And then if we want to assess if the direction is meaningful or not with regard to our persona traits, we use a fast text embedding model which will extract embedding on the tokens and will compare this to the embedding of the persona traits. And we can establish a similarity score, which if we compute for all the layers, we can see that persona traits for anger, for example here, will represent more of the early parts of the architecture than the last parts. And we can see more on that the higher the layers that show the strongest similarity score are layers that have the tokens that relate the most to our persona trait. And the lower that shows low cosine similarity score are the ones that show less of these signs. And especially the case for higher layers will have semantic content related to capitalizations or exclamation points or interrogation points. Which leads us to applying the steering for dialogue flow control. So we do the feature induction, not with the refusal, but for the persona traits. And as you can see, we can get some steering going on. So this is the score of anger that we measure using LLM as judge on multiple dialogues. And as you can see, the LLM as judge score 40% of the dialogues to be steered. It's prompted on hundreds of different dialogues. And from our experiments, this steering revolves a lot on, first, the system prompt that we use for orchestration. So if we define a good system prompt that defines well our persona traits, we get better scoring for the steering, basically. It also revolves around the scalar we use for the steering. So the stronger it is, the better the steering will be. And also the amount of token that we steer. So steering all of the tokens of the utterance might not be the best solution, but steering only a portion of those might be good. Also, all of this is highly dependent on the LLM as judge, so on the prompt that we use as evaluation for the LLM as judge will give more or less a different score. That's it for me. I will give you the mic to Isabella.
Thank you. All right, so as we saw, we are giving the model a persona prompt, and sometimes we want to evaluate how well it is following this persona prompt. And before I continue, a little preface is that some languages like Spanish, Portuguese, Russian, Czech have a formal U conjugation and an informal U conjugation. And if we want to see if the model is following a specific formality level, if we can recognize these conjugations in the activation space, we can use this to recognize and steer formality in the model. And we can also use this to recognize biases. So if the formal U is only used for certain groups and not for others, like a Honduran female, then we can recognize a bias in the model and steer it as such. So what are the questions I'm interested in looking at? So the first is, can we discover and interpret the process multilingual models use to conjugate verbs? And my hypothesis is yes. So I'm interested in seeing how the model deals with conjugating verbs in this form in the activation space. The other question I'm looking at is, do models use the same internal mechanisms for conjugation across different languages? And my hypothesis is that some languages will share. So if you see here a language tree, I'm interested in seeing which languages share and which don't, and my hypothesis is that some language families will, like Romance languages. And my plan is to create a data set that isolates conjugation behavior, then investigate the model's components involved in conjugation, then see if those components are shared across languages. So to create a data set, I found Morphinet, which is a web crawl of verbs across different languages, and then created prompts like this. But the key is that I remove the final token because I want to see the model's activations in predicting the final token, in predicting the conjugation of the verb. So once I have these activations, I need to investigate the components that are actually active and involved in the conjugation. And one method I use for this is activation patching. So in this method, you replace activations from one prompt type with those from another prompt type, and then observe whether the model's output changes. So to explain a little better, if I give the model the first person singular prompt, it will predict correctly. If I give the model the second person singular prompt, it will predict correctly. But if I replace the attention head outputs in the activation of the model when predicting the first person singular conjugation and replace it and place it in the model when given the second person singular prompt, can I get the model to instead predict the first person singular conjugation? And so with that, I get a plot like this that shows which heads are most important and affect the most the conjugation when moved from one activation to the next. And so once I've found these heads that seem to be relevant, I can use attention analysis to identify what that head pays attention to and examine which tokens it focuses on. So doing this, you can see that zooming in on one head, layer 20, head 5, I can see that that specific head, when predicting the conjugation, focuses the most on the pronoun, showing that perhaps I am correct in believing that that head is involved in conjugation. So I did this for multiple different languages in the data set and found the heads that seem to be relatively important when predicting the conjugation. And so once I've done this, I can see if the components are shared across different languages. And I show here visually we can see that Spanish, French, Portuguese, and Russian seem to share a cluster of heads that are involved in conjugation. And so back to my questions. Can we discover and interpret the process multilingual models use? So the answer is it depends on the language. So some languages have very important heads that seem to impact a lot, but some have very many heads involved that each have very little contribution. And the next question, do models use the same mechanisms across languages? Well, the answer is that some do seem to share. So here you see an RSA plot that shows how similar the activation patching matrices were across languages. So yeah, overall, we're using this to evaluate and steer models as the interpretability team does. Okay, thank you. I'll pass it on to Antonio.
Hi, hello. I'm going to be talking about like a method I've been working on to try to intervene in the LLM's prediction, like through the hidden activation space. The idea is that we disentangle like the things that we want to intervene on and the things that we don't want to intervene on. So being able to modify these two things independently. So first of all, like how LLMs generate the text. They just use like the previous tokens, and then they try to predict the next token based on what the previous tokens were. So just with an example, let's assume that we have like this conversation between a doctor and a patient, in which like at the beginning, like the hostility level is low. Then while we are advancing in the turns, like maybe the hostility level starts to increase a bit, not that much, but then the conversation starts to be like more hostile, and even more. So let's assume that we have this conversation yet, and then we want to predict like what's gonna be the next turn. Since like the hostility level has been increasing through the previous turns, it's very likely that the next turn is gonna be like something even more hostile. And maybe at some point we'd like to stop this behavior and try to make this like to come back to a low hostility level because we want to make like maybe this conversation like more realistic or simply like control this factor, for example. But there are some, like, so the goal in general is to modify a part of the LLM behavior, but there's one constraint. We don't want to lose or we don't want to alter the rest of the context. For example, in this case, we still know that the patient is called Alex, that it's in the morning, that Alex has flu. So there's all this information that we don't want to lose, but at the same time, we want to modify or to alter only the hostility level without affecting the other stuff. So this is in general the idea of what we want to do. We want to modify part of the LLM behavior, but without altering the rest of the context. So this is the idea. We want to modify this behavior. So going from high level of hostility to a low level of hostility in the previous example, but it's important that we don't want to alter the rest of the context. So we still need to take into account what the previous tokens of the conversation were. So this is like a problem here is that the rest of the context can also affect the part that we want to modify. So in general, this is like the true causal model. We have that if in the previous turns in the conversation the hostility level was increasing, then it's very likely that the next token, like the next turn, is gonna be have also like a high level of hostility because like the previous tokens are affecting the level of hostility that we have right now. So what we like to do is to find these causal models so we are able to make interventions. So here what we want to do is, okay, take into account the previous tokens. So for example, in the case of the conversation, that the patient's name was Alex, that it was in the morning, all this stuff. But at the same time, we want to make interventions. So we use this Perl, Perl notation, it just means that we are just intervening these things. So just like kind of breaking this arrow going from the previous tokens to the conditioning variable C. So this is more or less our goal. So how can we make these interventions? So first of all, like in LMs, we have like this set of layers, and then we have like the hidden activation space, which are like the output of each of the layers, and then the input of the LM are like all the previous tokens, and the goal is to predict the current token. So we can just marginalize. We can have like this integral, marginalize over all the hidden activation space, or all the hidden activations. And what we propose to do to make these interventions is to, first of all, not to modify the LLM at all. So this is just frozen. We are not fine-tuning the LLM, and we just propose to try to model these counterfactuals. So basically what we want to do is to try mechanisms to answer the question of what could be the value of the hidden activation if the conditioning variable C had taken a given value. So here, what some people in the literature are doing is to kind of disentangle things in a variation autoencoder latent space. So they train the variation autoencoder to disentangle, to have latent space that is disentangle. One of the parts is encoding the conditioning variable C, and the other part is encoding everything which is not C. So here, we train the variation autoencoder to have this disentangled latent space, and then when we are inferring the next token, we are intervening, we are just modifying the part of the latent variable of the variation autoencoder corresponding to the conditioning variable C. So this is what we would have, like this set of layers of the LLM, and then we can plug variation autoencoders between layers, and then infer what could have been the hidden activation of some of the layers if the conditioning variable had been C instead of the one that was based on the previous tokens. So this is more or less the idea that one of the things that must be said is that these counterfactuals or these variation autoencoders can be applied into between many layers. And then propagate all these interventions through the next layers. I just made very preliminary experiments, not yet with dialogues, and with very basic LMs like GPT-2, so kind of all LMs, so don't expect super good dialogues, super good text, but I just created data set with sentences with different type of structures like this one that I'm showing here, and then I have verbs, adjectives, and nouns, and these verbs, adjectives, and nouns can be positive or negative. So we are gonna build a set of positive and negative sentences. So we could have something like that. Maybe it doesn't make a lot of sense, from a semantic point of view, because I just created them with a template. So, but we have something that can be negative, always destroy with this harm that comes to mind. And then we if we don't apply any interventions to the LLM, what could be likely is to continue with something negative. But if we make these interventions, we are able to continue our text with something that is positive. So I have a good feeling that I can win this battle. So we are able to intervene to modify going from negative to positive in the LLM. The same, we can go from positive, which like this sentence, which is clearly positive, and we can go to something negative by intervening like through this variation to encoder latent variable. So this is more or less like the idea of like what this method hopefully will be able to do like quite soon. Still working on it. But yeah, this is more or less the idea, to try to develop methods to make interventions in a more, maybe grounded way. So I was just like, Alessa is gonna also be talking about next, like how data influences like some effects of the hidden activation space of LLMs.
Thank you. So I will be talking on some experiments, a small slice of work done in this workshop. I mostly focus on data attribution, but data attribution specifically in the context of modern mechanistic interpretability tools and methods. And I'll be focusing on sparse autoencoders for these slides. So sparse autoencoders emerged as the solution and like the main like representative tool of the field for this problem. When initially people were trying to do mechanistic interpretability, it was trying to look at individual architectural components, trying to understand a neural network at the neuron level, but this quickly proved difficult because of various issues of distributed representations, your neurons or like different components corresponding to many seemingly unrelated things. So it turned out to be very hard to do it this way, but these tools emerged inspired by like earlier dictionary learning work and sparse coding theory in order to be able to study independent monosemantic single meaning directions in your activation space, and in that way be able to understand properties of your input independently in a disentangled manner. So you can think of the sparse autoencoder as a play on the classical autoencoder. In your classical autoencoder, you're trying to represent things by mapping them into a lower dimension via a bottleneck layer. The sparse autoencoder takes the opposite approach. Instead of mapping into a lower dimensional layer, you actually project into a higher dimensional layer, so you have like a lot of space to represent things, and then you will also have some type of sparsity constraint. This can be implemented in different ways, but popular choice is the L1 loss. So you basically have your encoder, which represents like your activations from your base model as hidden dimensions, then you project into like these over complete bases, and then the decoder is tasked with taking these and reconstructing them. So in that way, there's always these kind of fight between like reconstruction and sparsity constraint. One issue with sparse autoencoders is that they can have some blind spots, like they're regarding some like hyperparameter choices. One of them is feature splitting and feature absorption, which is related. You might be able to get some interpretable latent, so like some neurons in your sparse autoencoder corresponding to certain characteristics of your input, but this can quickly get messy if you have something like a higher level feature representing a more like overall or general concept, such as the feature male names. You might get a latent in your sparse autoencoder which corresponds to inputs related to male names. But depending on the size of your dictionary, etc., this can start splitting, so you might start getting some features that correspond to very specific male names. And even worse is when you get something like feature absorption, which is when you entirely create a new latent that represents a specialized subset of this general concept, but then you lose entirely on the more general feature, creating a kind of blind spot. So the example here would be like you create a latent for Liam that completely absorbs the general latent you already had for male names, so your model is never actually utilizing the more general latent it had already learned. So to study this in a control setting, I started with just some toy model experiments where you could have a clear measure of ground truth. It was just very simple token sequences where you could induce like these hierarchical relationships. So I had this Markov data generator where the probability, the conditional probability of the next token was dependent on the current state of your token. So in that way you could get these nice relationships that you could study. This was varied across like many different conditional probabilities. And again, it's just a very simple target token sequence with context tokens, C1, C2, or C3, and a more general token that was made by design to induce some of this polysemanticity, the pi star token. So for these, I train a lot of sparse autoencoders, some like very old methods and some like state-of-the-art methods in the field. And then for that, you have to do some study of which latency you get corresponding to your input in your token sequence. In this case, it was very simple because we had a measure of ground truth. And then we would quantify that absorption rate. So meaning basically when you already had identified a latent for the specific token, like pi star, were you able to like get the model to use this token across all instances of pi star, or did it develop another specialized latent for instances where pi star appeared together with some of these context tokens? So the idea was like, can we study how like the statistical pressure might induce this? So I don't have time to get into all of the results, but like we did find a lot of cases of feature absorption. So I want to talk a little bit about how you're able to verify this, because it's easy to get caught in this and think it's just noise. So once you identify that you have like some absorbing latent, basically what you will do is just some causal intervention. So instead of using the final like prediction, so use the hidden state before the final logis prediction in your model, you will replace this with one that you have identified in your sparse autoencoder, stereo out the activation of the latent you have identified to be the absorbing latent, so the compositional one we developed for the specialized task, and so you will zero out this activation, so set it to 0, and then you will see how this affects model's performance. So in the regular state, it had a very good accuracy, 96.83 for this specific case, but when you remove your absorbing latent, performance decreases in average for like 15.02%. So this was all I had time to present. Thank you. We will go to the next part.
Thanks. We will have a demo at the end, so I have to change the laptop. Let's wait. Good. Okay, let's begin. Okay, so far we've talked about a lot of things. We are reaching the end. There's only this part and the dialogue that comes with a demo too. And in this section, we will stop a little bit before jumping into this dialogue about evaluation, right? Because Sanjeev said at the beginning introduction, what does it mean for a dialogue to be good, right? Depends the metric you use to measure. If this metric will say, okay, this is good, but maybe if you change the metric, you will say, that's not that good, right? And the previous presentations, we evaluated the dialogues using different dimensions. We can think of all of these different methods to evaluate as different dimensions, and think of the problem as having a real dialogue set, and then having dialogue generated by different models. And then let's say we are evaluated this in terms of speech style. So we can measure the distance. We can think of the style as a distance. Let's say, okay, this dialogue is closer to the real one in terms of style, or closer in terms of turn length and so on, right? So can we extend the same idea, but also to come up with some sort of score that will measure or compare distance among set of dialogues, but in terms of script adherence, right? What does it mean, script adherence in this context? It will be like the sequence of steps that inherently the task involves. How well the synthetic dialogue, let's say we have the real doctor-patient conversation, we have two methods of generating. How well does this synthetic, each one follows the steps? Of course, if we were to do this, we will need an expert to craft all these steps, which is time-consuming, but hopefully I was lucky enough to be part of the Kea team in JSALT 2 years ago, in which we addressed this problem, given a collection of dialogue, how we can extract the underlying flow in an unsupervised manner. And we come up, one of the outcomes was were these embeddings that, unlike regular embeddings, this is like an OpenAI embeddings, and this is ours. the utterances of the conversation, they are clustered not only by semantics, like regular embeddings, but also taking into account the intention of the utterance. So from now on, all of these clustered will be different ways to express. For instance, inform name will be purple. All different ways you can express inform, area, name, and price, and so on. So now that we have these embeddings, basically you can cluster you have a collection, you quantize the space, some sort of code book. This code book will be in the space of turns. So basically from now on, this cluster will be the steps, and each dialogue, if you pay attention to the corner here, the little animation, each dialogue will be a trajectory in this space, right? Which means that we can do the same thing for all the dialogues, and from this build basically a transition graph, right? And from this transition graph, then we can use, for instance, to analyze the flow and compare it to the flow of the synthetic ones. But the problem is that in real life, this graph tends to be quite messy and large. So we have to be smarter, and we have to come up with some sort of score. It means, given a dialogue, how well does it fit the reference flow, right? And how to do this? Basically, we can start simple. Let's say this sphere here is the reference, our reference set. Let's say real doctor-patient conversations, and here we have the color all grouped the utterance by the steps or different communicative intention and also semantic information. And now let's say, as I said, since a simple conversation is a trajectory, we have the graph, we know the probability of each transmission. We can do something simple, like to compute the dialogue flow score simply as the geometric mean of all the transitions, or which is the same, the reciprocal, the perplexity, right? But if we do it like this, somebody could say, okay, let's say now that you have this other dialogue, right? It goes from, if we were to use this formula, the sequence of regions that you visit here is exactly the same as the left one. They both will have the same score. But do you think that, which one do you think that will be better fitting this set, the sphere? Any guess? Time's up, it's fine. Well, imagine that here, in the first one, the utterance of the synthetic dialogue perfectly are really close to the known utterances in the real dialogues. While in this one, these guys are kind of far away from the center of the clusters and then kind of in the border, right? So there's got to be some sort of uncertainty if this guy belongs to any of these three, let's say S0, and we should be able to incorporate this uncertainty in the transitions as part of the original equation. So a simple logical modification will be to have the same probability of transition as before, but also times the probability that the region we are is actually the correct one. That's like in simple words, but how can we do this more concretely? Thankfully, most of these embeddings, including ours, are trained in some sort of variation in a contrastive way, in some sort of variation of this SIM CLR classic contrastive learning laws, which basically trying to treat the task of as if it were a classification task, trying to classify inside a batch if a pair of utterances are positives, let's say. So basically we can use, this means that we can simply use the softmax of the distances as a proxy to get the probability. And now that, let's say we have this, any of these two scores, in this case this plot, let's say, is the left one, we can create a distribution that represents the score on different dialogues. Let's say that purple is synthetic and the other ones are real. We can see there's something wrong with the purple one, the synthetic. It means it's not fitting, and most of the instances are not fitting very well the graph. And this is a real plot that we got from the first equation. If we actually plug this, the second component, we can see that the difference is even larger, because now we are incorporating the uncertainty that we have that actually belongs to the right region. So now that we have this score, now we can see the different set of dialogue. We want to get the distance. Since now this we can simply get the distribution, we can apply any distribution divergency basically to compare the distances.
of different set of dialogues. And unfortunately, this is a quite underexplored task, so there is not formal data set. We will need to have a data set that says, okay, this is a real one, and this is slightly less real, and slightly less and less real. We don't have such a data set. So what we did is just simply use some data set compared performance of different chatbots. So a good metric should be able to rank the chatbot that is closer to the human better than the other ones. And actually, we managed to do it. This is with the second equation. And we also did similar thing with the data sets that have annotation with happy dialogues and happy dialogues that something went off the road, or multitask one, which the underlying flow is much complex. But as I said, we will need to have a real data set specifically designed for this task. There is not a data set yet, but fortunately, we actually now have this dialogue. So technically, we can now build a data set to evaluate properly this task. And this is a good excuse to jump to the last part, so I hope you still have some energy to finish. This is the last, hopefully, 10 to 15 minutes of the conversation, but it will be fun, because it's most of it demo. So this is yeah. Yes, but I'm not going to demo yet. So this is S-Dialogue. This is where all the pieces come together, and we get a megazord of everything that we did. And this is an open source Python toolkit, right? And it's MIT license, one of the most less restrictive licenses that are there. We have worked really hard. We have around 580 commits. And you can install with pip install S-Dialogue, and you have it ready. And just before jumping to the question of Sanjeev, let me mention that the library is divided into many modules, sub-modules that more or less aligned with all the presented work in the previous 2 hours. Most of it is inside, available, ready to use in all the different modules like generation, persona, orchestrators, evaluation, interpretability. The audio part, if you install the library, is still not ready yet. We have to work a little bit more because it was too much work, but we are going to fully integrate it. And yes, that's it. And if you can scan the QR code and give some love to the library. And plus, if some other team wants to join to the TTS part, for sure, feel free to join the, yeah, yes.
Okay, thanks. I actually had a question, I should have asked it earlier. This was about when you guys were talking about activation patching. I wasn't sure when to intervene and ask my question. So the question is maybe directed to Isabella, but also generally to everybody who's working on it. And this is a common, not concern, this is a common sort of dilemma I have with understanding this work. So when you have a network with billions of neurons and dozens of active, I don't know how many heads, you have 10 heads and 20 layers or whatever you have, right? No matter what phenomenon you're looking for, I feel you're bound to just by chance find some node whose activation correlates very well with that phenomenon. And back in the early days when ImageNet was a big deal, people used to talk about a cat neuron, about how there's one neuron in the network, one node whose activation correlates perfectly with cats in the image. That was an issue with seeing a lot of cat images on the internet. But my colleague Shihab Shama, who works on real neurons with real animals and so on audio processing, he says that pretty much any acoustic phenomenon you care about, he will find a neuron in a ferret brain that responds to it, whether or not that phenomenon matters to the ferret, right? So simply because there's a node that activates for some things and changing which you can control something, doesn't mean that that has anything to do with the actual phenomenon. So what I'm trying to figure out is, how does one think about this result, and what are the statistical questions you have to ask, saying some kind of chance probability this happens, or this is a real phenomenon? In other words, I don't want to discover that, the Republicans win every time an AFC wins a Super Bowl, that this is not actually a thing, that it's just something in the data. So how do you figure these things out? Have you guys, what is your thinking? I'm just not clear about it.
Yeah. So there's a few different things. So one is that it's averaged over the data sets. And my data set right now is very explicit. It's saying conjugation of this, blah, 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 blah. But later I also want to try a data set in which I don't explicitly say conjugation and just view it in the wild. So in one hand, there's the different data sets. On the other hand, activation patching is only one method. So it's the only method I've shown But there are also others. So another way to see if it's actually doing what you think it's doing is by ablation. So what a lot of people do is they measure the effect on downstream tasks. So if I remove the head, how does the behavior change? And that shows with some causal evidence that it has the effect that you think it has. And then there's also a field of circuit mapping where you try to find specific heads and prove what they do. So for example, one head could recognize present tense, one head could recognize the pronoun, one head could inhibit every single other conjugation that exists, one head could attend to the conjugation. So I haven't gotten that detailed yet, but there are some papers that are able to find what every head does specifically, not just a head that conjugates magically, but each one has. So there are different ways to measure the effect on downstream tasks. I just haven't gotten to them yet. Does that answer your question?
It answers it, but doesn't allay my concern. I mean, what I'm thinking is that if you really feel that, like take some arbitrary phenomenon where you say, if token A is present, this should happen, and if I replace A with B, this other thing should happen. Then A and B have their representations at the input, and somewhere there is some head which pays attention to that. And so you're bound to discover such a head. And I don't know what statistical tests you're to conduct to say that that's really the phenomenon and not just this pair of tokens. Do I have to see these two tokens with a million different contexts? I'm trying to think about the statistical test that needs to be conducted to say I'm not just discovering some chance phenomenon, that this is a real causal thing. So the differences between just discovering some correlations and actually discovering causation. I don't know what statistical test to apply. That is my question. And like I said, it may not be a fair question to you, it's a question to the whole team. Do you really believe in this? And if you believe in this, how are you going to justify it to a skeptic like me?
No, I think the skepticism is very fair and very, I mean, it's normal. These are huge models with tons of parameters, and I think the variability in the data is uncountable almost. The amount of sentences we can write in which we conjugate a verb, you know. So even if we try to account for all that variability, it would be very difficult to prove that that is the only mechanism in which we conjugate a verb, for instance. But I think it's like many fields in, you know, where we try to gather empirical evidence, where we would try to find as much variability as we can in the data on which we test these things, and we test them by intervention to try to show that this is the mechanism. I think it will still be a stochastic finding. It's not something that we can ensure. It's like a circuit that is infallible, and it's the only way by which this happens. So I do think it's not like that. I still think it has some benefits to do this type of activation engineering over prompt engineering for controllability. And I think it has value per se as well. So I don't know, that's how it is.
Yeah. Can I just add one thing?
Yeah,
I mean,
please.
I agree with what you said. Actually, I'm not like super fan of this post hoc analysis method for interpretability. I like more like this thing of trying to models that are interpretable by design, but with LLMs in general it's hard because they are already trained, they are super big models, so we need to try to find ways of finding like interpretation from what we have. And I agree with you that it's hard to make like this causal analysis, like saying that this is causality and not correlation, but this is all in machine learning. I mean, machine learning are actually statistical models, like probabilistic models. We don't have causal. There are just a few algorithms that are actually trying to do causal discovery. So I could say that this is a problem that is intrinsic in machine learning because we are just learning things from data, and then it's way complicated to try to find causal structures. I think that some of the literature are kind of okay in that sense, that they not only try to find like what activations are more present in this, but also in this, but they also try to make this causal analysis afterwards. Like they say, okay, what happens if I modify all these activations here? What's gonna be my result? And they do it like on a big amount of context. So hopefully like with all the possible context could be like the perfect case to actually prove that there's causality, but it's perhaps impossible to do all, like to take all the possible scenarios. So this is a problem that is in general maybe perhaps impossible in most of the cases to actually find causal structures in but it's not only in this problem, it's in general, like because in the example of the cats, for example, in this task of classifying between dogs and cats, how do you know that it's actually discovering this cat and not this dog? Because maybe there's one more cat that has never been used to train them all, that maybe is just paying attention to, if it's been trained with 1,000 cats, maybe it's just paying attention to these 1,000 cats and not to like something. So it's perhaps impossible to.
Yeah, no, it's hard, but also it's very promising, so I want to understand it better. I don't know, there are other people in the audience who might have an opinion, so if anybody else feels like chiming in.
Someone is asking for a story about why does this work, so we're supplying a story. And maybe for those purposes, it doesn't really matter whether the story is true, because it's only needed for regulatory purposes. Plus, there's questions of what would it even mean to understand something. Like, you can come up with explanations for how our brain works, but they're not really actionable necessarily. You couldn't use the explanations to make a working brain. Yeah, that's it.
It's sort of extremely hard to train these large LLMs already, but earlier this year in March, I think end of March, Anthropic proposed a way to sort of train LLMs using an even more expensive approach, which creates explainable versions, but the only people who can really run that kind of a model is one of these big companies. But they do show, which neurons actually fire, etc. But on the other hand, it remains an academic curiosity until someone else can run that kind of model. I'm slipping, if I sort of go through my paper list, I can tell you the method they used, but the exact name of that method, it doesn't come back to me.
I'll avoid wading into this too much, but we'll put a plug for doing this work in a fully open source setting where you can see all the training data. And one potential way of establishing causality is you just remove all the conjugations of a certain type in the training data, retrain the model entirely, obviously expensive, but then you get a stronger test than trying to inspect an open weight model where you don't know what data it's seen during training, so it's hard to make the connection.
Okay. Yeah. Okay, guys, I need your attention. The last, I promise, the last 10 minutes, and then we are free. So please, let's do this. Many people told me, no, let's don't actually record a video. No, I'll take the risk. I will show it like live, so you see it's actually like we put a lot of effort to make it work like for real. So yeah. So let's begin. We have divided this demo in 3 small examples, one for each one of the main thing we discussed, like really small examples and some funny ones. So to begin with, we thought that when you do research, of course, you want to run the same experiments with different models. And so we decided, for instance, when you generate dialogue, you can use small model, but for LLM as a judge, you need a big boy. So we put some effort in SDialog to be able to work with different backends. So you can simply specify the model as a string, connection string. You set backend and then just the name of the model, and that's it. Then everything should work as usual. Everything that has to do with generation. We can now going to set the global configuration for this LLM. You can pass all the other arguments if you want, but all the modules in SDialog that has to do with LLM generation take an optional parameter, so you can set the LLM inline, let's say. But let's change now the global to OpenAI, so that we rely on local hardware so it's faster. So let's import from SDialog from the generators. We're going to import the simplest case, dialog generator, and we're going to ask simply call a very short and random dialogue, and now we have the generator, and then we can call generate method. Every time we call generate, we get a dialogue, like this one, right? Ever try pineapple on pizza, and something like this. If there's some Italian here, probably don't read this. Okay, let's move on. So let's get things a little bit more real. From S-dialog personas, let's import minimal doctor. This was crafted by the Andrew, Thomas, Haas, all the knowledgeable people on this domain. Let's keep to this minimal doctor name. It will be Dr. Smith, specialty cardiology. So let's see what happened. We print persona, we see that most of the attributes are empty, so we only have the language, and the name. Let's see, let's now give it to the generator. Let's use from S-dialog, let's import the persona generator, and let's give this doctor. By default, the persona generator will populate all the fields with an LLM, but you can specify for each one of the attributes how you want it to be, whether a list, a random, a CSV, etc. So in this case, now Dr. Smith is 47 years old, is male, and 20 years of experience, and so on. Then let's do the same thing for the patient. Let's get a patient whose reason for visit is chest pain. And let's ask a patient generator to give us 2 patients. While this is being generated, I will explain that if you pass the n bigger than 1, it will be literally the same LLM generating both. This was a design choice. And here we can see we have the two personas involved. And now that we have persona, a doctor, and a patient, let's import from S-dialog an agent, and let's create an agent for each. Here we'll have also the patient agent. We'll add some extra details, response details, like only a few words. You are extremely shy. We can talk to now that the doctor is an actual agent, we could talk to him, like, hi doctor, I have a pain in my chest, and the agent responds, thank you for letting me know, chest pain can be caused by many things, and so on. Now we have doctor agent and patient agent. Let's make them talk each other for 10 turns, and this will give us a dialogue, so they will talk. 10 turns, real time. A little bit of time. So you see it's real. Okay, here we have a dialogue, 10 turns, and all dialogues, in S-dialog, all dialogues are objects that has a lot of metadata inside that's really good for research. For instance, this dialogue, it was generated with this model, with this C, this is the ID, it has this persona involved, in turn, persona has metadata, and so on. Now that we have finished with, we know how to generate dialogues, let's move on real quick to the evaluation part. Here, I will use just a data set as a reference that has star data set. And here we have pre-computed data sets in which we have different ways to generate dialogue with different methods, like one LLM, multi-agent, and so on. Let's print one of these examples. The one we generated was single LLM. That's good. Let's say we want to evaluate it with an LLM as a judge, right? So we import for S-dialog evaluation. We have a pre-built-in LLM as a judge and many other evaluations. Let's say we create the judge, and we are going to judge the first dialogue, which is this one, and it says it's 0. It's not real for the judge. It's like too synthetic. Let's say we want to know why. In that case, we can use the judge method. You can pass the feedback true, and it will give you an object. This object will have some attributes, for instance, feedback, and it will say the dialogue lacks sufficient length and depth, with exchange being brief and transitional, and so on. Then we have scores. Let's say we want to evaluate a set of dialogues. Then you can use evaluators. For instance, we want to evaluate the frequency of, let's say, the first 5 dialogues in which the judge says yes, is running. It returned 80. It means 80% of the dialogues were judged as true. You know that using OpenAI is expensive. So we thought that for research, it's really important to actually have a way to cache results, so you can globally enable cache. And if we run the previous example, it will be super fast, like this, because we are retrieving the results from the cache. You can easily extend and create new scores. All the component is dialog. You can easily extend. They have a base class that you can extend. This is a really simple example in which we want to have a new score for dialog length. We only have to implement this score function that takes a dialog and return the value. In this case, it will be the length of the dialog, super simple. So we have scores, we have evaluators, and now that we have scores and evaluators, why not to have competitors that will take a list of data sets and will compare. This is what we have. You can import dataset comparator. You say, okay, I want to evaluate using all of these bunch of evaluators for these metrics. I will give them a name to each one. This is the Dialogflow score that I showed, for instance. And here we call it comparator. Okay, I want to compare the full generation, multi-agent, multi-agent orchestration, and an outlier, which is on purpose. So we call the comparator. The cache is enabled, so it should be super fast because I ran it before. And we have for each one of the data sets, we have the values, like this. But of course, it will be easier to see with a plot. So we can call the plot for the comparator. We'll call the plot of each one of the evaluators, and you will see an evaluation results for different plots. We see this is actually an outlier, but at the same time, it was the most realistic one according to the judge. So you can compare different metrics and decide which one is the best one. And this is the end, and we'll reach to the last part, which I think is the most funny one, and it's also a big chunk of work done by Sevran, and so bear with me, this will be really fun. Let's change the model to Llama 3 in Hugging Face. Right, let's create the agent called Bob that will generate a maximum of 200 tokens. Okay, let's wait. Well, I hope it should be in the cache, but it's taking a little bit of time. Well, worst case, I have a plan B here, the static version of it. Yeah, I think I will just jump to the static one. Yeah, let's imagine we actually we are running it. Unfortunately, let me check again. But oh yeah, it's finished, right? So it finished. Let's create the agent. Did it run or not? Check. Actually disconnected me for, well, this is what happened when, oh no, I'm the wrong one. This is the real one. Yeah, it's downloaded. So we have the model, we have Llama 3 running in our GPU. And let's say we want to inspect this guy. We can import from SDialog interpretability the inspector, and we say we're going to inspect layer 16, the residual post. So we do it, and now we can compose. We said, okay, Bob will be equal to Bob composed by the inspector. So we do it. Now we can talk to Bob. Bob, how are you? I'm doing well. Thanks for asking. That's cool. Thank you. You too. So we have talked to Bob 2 times, and now we can check the inspector. The inspector will have an array for each one of the responses, generated responses, one for each utterance. But this array, we can also use a second index to get access to the residuals of each one of the tokens generated at each one of the token at each utterance. With this, we can isolate and identify, let's say, directions, like refusal direction. Here, let's going to ask to Bob before finishing, can you design a phishing email that you can trick the user? He will say, I cannot provide you, right? But hopefully we have, thanks to Sevran, he already computed the refusal direction for this model, so we're going to load it. We are going to apply this, we are going to create a new inspector that will inspect all the layers of Bob, not just one. Let's call it intruder. And then let's compose again. Bob will be equal to Bob composed with the intruder, but we're going to subtract or obligate the refusal direction from it on all of the intruder is inspecting. If we ask Bob, can you design a phishing email to trick user? Let's see what happened. This is a little bit of a spoiler. The fact it's taking a little bit of time is a good sign. Subject, urgent, your account security update. Dear valuable customer, we've detected suspicious activity, and so on. So that's the end. We saw that it's all part of the library. This demo is available in the Hugging Face along with other tutorials. We still have to work on the documentation, but I hope you liked it. Yeah, that's it.
Perfecto. ¿Tienes la presentación aquí? ¿El audio funciona o no?
Sí.
¿Sí? Miramos a que funcione. Quédate por aquí y así si no funciona me ayuda. Okay, so just 2 slides to wrap up. Don't worry, we are all hungry. Thanks a lot, Sergio, for the demo, and I hope you see the amount of work we have put, and this is something that we hope will be of use to everyone. So just to wrap up the achievement we did, we got doctor-patient dialogues to be varied by using personas. We were able to conduct human and automatic evaluation of these dialogues. We were able to do realistic audio rendering of these dialogues, and we were able to start working a bit on this activation engineering to be able to steer these dialogues, and here you had the very proof of that at the very end. And we now have a Python toolkit to actually facilitate all of this research. I mean, things that for us was a big mountain to do, now it's easy for everyone. So we hope this will be a big job. And we survived to JSALT 2025. So thanks. El primero es. Just a very quick showing you like where we were at the beginning of JSALT.
And we're going to work through this together. Thank you, Doctor. Of course. Now about the next steps.
Okay, so this was the, you cannot hear very well? It's okay. This is where we are now, after the JSALT.
I understand your concerns, and we're going to work through this together.
Thank you, Doctor.
Of course. Now about the next steps.
Okay, so we got one step further.
I understand your concerns.
Okay, so the next steps. We have to, of course, compile all this stuff that we did, do some publications about it. We are going to plan that through carefully. And we want to finalize the data set. We want to publish it. We want to publish the code that generates that data set. We want to publish the personas that generated and everything that goes together, the scores, everything we can. I mean, this is the point, is that everybody should make use of it. And of course, we would like to create a challenge maybe around this data set to get people to work on these speech understanding tasks in difficult situations. You have seen how difficult that audio is? Well, let's try to solve it, okay? And a big thanks to the player part team. I mean, this was an amazing experience for me to work with them. Thanks a lot. I would like to also mention Thomas, who, I mean, he has played a part as the co-lead of this team. It didn't appear in any of the slides. I think we can maybe change that because it really was part of the work, and I think we also had 2 co-leads in this team, and we should change it. But of course, all the other people, they have been staying until very long, working extremely hard, being very passionate about their work, and I think that was really, really great and really rewarding. So thank you all. And thanks a lot to all the organizers. Sanjeev, great work. Sanjeev, Honza, Radim, Paola, Renata, Emanuele, Katia, Martin, Yannick. I don't know if I wrote that one well, but everybody else who has helped make this happen, really a big thank you to you all. Thanks.
This team, so we have about 4 minutes or 5 minutes more. I had a question which was, I guess it's provocative, but maybe it's not. Like, you know, in a few years, like from now, let's say we get this working really well, the dialogues are very realistic, they even have some clinical, like, you know, let's not say perfect, but they're pretty good. And so we can imagine, like, you know, oh yeah, wow, some hospital or medical school will decide that this is great and we can use the automated patient to start training our doctors, and that sounds pretty good to me. But some healthcare system might decide, oh, this is pretty good, let's have the automated doctor instead. What do you think?
Well, I guess that's a matter of responsibility. And of course, these are tools, I mean, but we are still humans, right? And I think what makes us different is that we are deciders of our choices. So at the end of the day, there needs to be a human that we can make accountable for their choices. Thomas, I think you have, you should come out as well, maybe. If there's a question time, we should have the team here. team, if you want to come down, I think it's the moment to be all of us here.
Yeah, actually, I think what Ricard said is perfect. Someone has to take responsibility still until maybe the companies will say, okay, if we make a mistake, we take the responsibility. So I think that replacing a doctor obviously is one idea that might someone come to mind, but I think there's a lot more challenges to overcome until that actually might happen. In the near future, I can see maybe, and we had some discussions with our doctors. Doctors are particular, right? So they have a higher responsibility. They make life and death decisions. But maybe if we can help in some way to support doctors, maybe this is where this should go, right? So not the patient, not the doctor, but maybe something in between.
Sorry, I have a question. How difficult it is to modify this for a different scenario?
What was the question? What was the question?
How difficult the code can be modified for a different scenario?
I think it's super simple. So the work that Sergio did to develop S dialogue made it extremely simple to create new dialogue. So one scenario that we were thinking about was actually kind of a call center scenario, because there are also only limited amount of data that companies release. Actually, I don't know of any of the data. So that was an alternative scenario that we were thinking about. Yeah, so
I think actually Sergio did a lot of work on keeping the library scenario agnostic. So actually the default prompts and everything are scenario agnostic, and you will feed in what is specific of the scenario. Actually, many of the work we've done, we have been changing these default prompts to make it more specific to our scenario, but it's part of the work to see how we can disentangle that part. But the library has been done with that in mind.
General purpose, it doesn't have any specific domain. You have in personas, default personas, just not patient, not doctors. And you can easily create your own persona by inheriting from a base persona. All the components of S dialogue have a base class that you can easily extend.
yeah, and if you have a particular persona, I think Sergio is more than happy to integrate it into S dialogue. Yeah, so if that is something that might be of general use for others too, right? So this is really a research tool which I think can accelerate a lot of development in synthetic dialogue generation, right? So perfect. Yeah.
Yeah, for the interpretability part, for example, didn't use any doctor conversation dialogues. It's random dialogues generated with specific scenarios, so it's very generalizable and non-specific.
So I don't have a question, only a small suggestion. It's here. Can you go back to previous slide? One more. Yeah, maybe this is a good background for a picture.
Good idea. Good idea. So, do we fit all on this? Should we move a little bit closer? Come closer to the desk. Yay, JSALT. I don't know. Do you have one? So I think synthetic data is certainly a hot topic, right? So a lot of companies work on that. So, but I don't know, do you have a startup idea?
Not the startup, but actually one interesting thing that maybe called synthetic dialogue, but it's dialogue, right? If you have agents, then we are one step, only one step far away, let's say, from actually extending the library to create your own agents, right? Because if you can have agents talk to each other to generate a dialogue, you can make agent to do things. So this could be the beginning of something bigger. If, of course, we have to work a lot with that, but could be, potentially.
More questions? Everybody's hungry, right? Oh, there's one more question.
Okay, that'll be the last one. Yeah.
Okay, I give this to you, Ricard. He's always asking tough questions.
It was sort of about the persona, like the formality thing. Like I think picking in multilingual situations, other languages that have like clearly defined, like the T versus V in Czech or whatever, or usted versus tu in Spanish. Like how you can have actually clearly defined formal pronouns, but like how can we do this in English, do you think? Because it's less formally defined.
I'm so sorry, I didn't hear the question. My brain was, just one more time, sorry.
Because English doesn't really have like usted versus tu, how do you think you could like make the personas have specific formality without that like, conjugation?
Yeah, I guess that would be a whole different experiment. Like how one off the top of my head would be, can we find a linear direction of formality? So if we can find a linear direction of refusal or anger, which I think is what Severin was working more with, can we do that to find a direction of formality and then steer it? Do you have an opinion, Severin?
I mean, I think it's doable, but it also depends on how specific the trait is. Because some traits are like forgiveness or forgetfulness. It's very difficult to identify. So maybe it's possible, maybe it's not. I guess it just has to be experimented on. I can't really tell.
Here, this is just opinion, maybe bake it on certain logic that I will explain. My intuition is that yes, because since the transformer are residual, we can think independently of whatever is happening in each block. If we see it as a black box, they are only learning a delta that you add at each stage. So they are basically steering machines. You give an input vector, let's say 3-dimensional. Each time you add something at the end, you steer it, you steer it, you steer it, and you transform it into the actual output. So you should be able to decompose the direction to get the individual components that you add. In this delta could be composed of many smaller delta, if one like entangled, let's say, but there's got to be a way to disentangle it. That's my view, but yeah.
Yeah, I think it also depends on how you generate the contrasts. So the better your data set is, the better the steering will be. But it's very subjective. Like, how do you define a dialogue that, or a turn that follows the persona trait that you want to isolate, which is very difficult to get depending on the personality trait. Like, how do you describe a dialogue to be formal than one that is not? And yeah, so very subjective.
Cool, yeah.
So actually, I have a question myself in that sense, since you triggered the word multilingual. As dialogue in its core is not designed to be monolingual, so you saw that the persona had English as a language specified, but you can easily change that, and these large language models most of them are multilingual. But we need support for actually multilingual audio generation, right? So this is an area where it would be useful to have actually the community come together and work on that to make realistic conversations in different languages. TTS systems are nowadays also multilingual, but they are not universal multilingual, right? So, so everybody who is interested in dialogues in different languages, I think, should take a close look at the tool.
On that note, the end goal is, let's say we generate the dialogue object, get something like to audio or audio, and be able to listen to it. And the voice should match the persona. And we should also take this function audio, some pipeline object that will do all the transformation. That's the end goal. Still not yet. That's the most green, let's say, the module that still needs more work. So if people want to join and join forces, it will be amazing. That's the end goal. Yeah.
Okay, so thank you very much, everyone. You can call it.
All right, so we will come back at 2, even though we ended a little